Hello there, and welcome. Tonight I want to take you somewhere far beyond the reach of city lights, beyond the familiar boundaries of our everyday world, into the vast and silent darkness where ancient travelers drift through the cosmic night. I want to tell you a story about something that appeared in our skies not so long ago, something that at first seemed like just another discovery among countless others, but which might actually be an echo of something much older, something that was perhaps known long before we thought we found it for the first time. It's a question that might sound impossible at first, the kind of paradox that makes you furrow your brow and wonder how something could be known before it was discovered. But what if I told you that sometimes the universe keeps secrets in plain sight, that it writes its mysteries not in hidden codes but in patterns so vast and slow that human lifetimes are too brief to see them clearly? What if the comet we call Atlas, which graced our skies so recently, was actually returning to us like a familiar ghost, following a path that was witnessed and recorded generations ago by people who looked up at the same stars we see tonight, but lived in a world lit only by candles and oil lamps? As you settle in tonight, perhaps pulling your blanket a little closer, adjusting your pillow just so, I invite you to join me on this gentle journey through time and space. We're going to explore a cosmic mystery that connects us to our ancestors who stood under these same stars, to the ancient ice that drifts in the outermost reaches of our solar system, and to the profound realization that we might be witnessing not separate events scattered across history, but chapters of the same long story, written in orbits and ice and the patient passage of centuries. And by the way, if you find yourself drifting off to sleep as we explore these cosmic wonders together, that's perfectly fine. In fact, it's wonderful. Let these thoughts carry you into peaceful dreams where you float among the stars, because this story will still be here, unfolding in the darkness, just as these celestial objects continue their eternal dance, whether we're watching or not. You can always return to any part of this journey, just as these comets return to us across the vastness of time. Consider for a moment the darkness between the stars, not the aggressive darkness of a cave or a closed room, but the gentle, infinite darkness of space, where silence isn't the absence of sound, but the presence of a peace so complete that it has existed since before the earth was born. In this darkness, things move. They move with a patience that human minds can barely comprehend, following paths that take them on journeys lasting thousands, millions, even billions of years. These travelers carry no lights of their own, at least not while they drift through the cold reaches far from any star. They are invisible, unknowable, until that moment when their path brings them close enough to feel the warmth of our sun. And then, like flowers blooming in cosmic slow motion, they begin to glow. In the early months of 2020, while the world was beginning to grapple with changes and challenges that would reshape our daily lives, something was happening in the depths of space that most of us didn't notice at first. A faint smudge of light, barely distinguishable from the countless stars that pepper our night sky, was picked up by the automated eyes of the Asteroid Terrestrial Impact Last Alert System, or ATLAS, a network of telescopes in Hawaii that spend their nights scanning the heavens for objects that might one day cross paths with Earth. The system found something on March 28, 2020, something that would eventually bear its name, Comet C-2019-DY4, though we would come to know it simply as Comet Atlas. At first, there was nothing particularly remarkable about this discovery. Comets are found regularly. These ancient chunks of ice and dust that drift in from the outer solar system warm up as they approach the sun and develop those characteristic tails that have inspired wonder and sometimes fear throughout human history. But Atlas began to do something interesting. It began to brighten, not dramatically at first, but steadily, promisingly, in a way that made astronomers around the world take notice. The calculations began, as they always do, with a new comet. Where did it come from? Where was it going? How close would it come to the sun? How bright might it become? The answers to these questions were intriguing. Atlas was on a path that would bring it relatively close to the Sun, close enough that some predictions suggested it might become visible to the naked eye, perhaps even spectacular. In a world that was suddenly spending a lot more time indoors, looking out windows, seeking connection with something beyond the walls of our homes, the prospect of a bright comet felt like a gift from the cosmos, a reminder that the universe continued its ancient patterns regardless of our earthly troubles. People began to watch, to wait, to hope for a celestial spectacle that might lift our spirits in challenging times. But as astronomers studied Atlas more carefully, as they traced its path backward and forward through the mathematical machinery of orbital mechanics, something curious emerged. The path this comet was following wasn't entirely unfamiliar. It bore a striking resemblance to another path, one that had been calculated and recorded long ago, in an era before computers, before photography, when astronomers worked with pencils and paper and careful observations made by eye through telescopes that would seem primitive by today's standards. This other path belonged to a comet that had been one of the great celestial spectacles of the 19th century, a comet that had blazed across the skies in 1844, bright enough to be seen in daylight, trailing a tail that stretched across a significant portion of the sky. Now, you might think, well, space is vast and comet orbits are elliptical, so perhaps it's not so strange that two comets might follow similar paths. After all, there are only so many ways an object can orbit the Sun, aren't there? But the similarity between the orbit of Atlas and the orbit of the Great Comet of 1844 went beyond mere resemblance. When astronomers overlaid the two paths, accounting for the gravitational perturbations of the planets, accounting for the slow drift of orbits over time, they found something that made them pause and consider a possibility that was both simple and profound. What if these weren't two different comets following similar paths? What if they were fragments of the same comet, pieces of a larger whole that had broken apart at some point in the past? This idea, that Atlas and the Great Comet of 1844 might be siblings, opens up a window into the deep history of our solar system. It suggests that somewhere in the past, perhaps thousands of years ago, a much larger comet made its way toward the Sun. As it approached, the stresses of solar heating, the tidal forces of the Sun's gravity, or perhaps some ancient collision caused it to fragment, to break into pieces that continued to follow essentially the same orbit, but spread out along it like a string of pearls, each piece returning to the inner solar system at its own time, decades or centuries apart. Think about that for a moment. When we look at Atlas, we might not be seeing a new visitor at all, but rather the return of something that has been here before, not in its current form, but as part of something larger, something that our ancestors might have seen, might have wondered at, might have woven into their myths and legends. The Great Comet of 1844 caused a sensation when it appeared. People gathered in streets and fields to watch it. Newspapers wrote breathless accounts of its beauty. Artists tried to capture its magnificence in paintings and sketches. And now, 176 years later, we might have been looking at its sibling, another fragment of that same ancient parent, returning home on the same well-worn path through the cosmos. The story becomes even more intriguing when we consider what happened to Atlas as it continued its journey toward the Sun. Through March and into early April of 2020, the comet continued to brighten, raising hopes that it would become the naked eye spectacle that astronomers had predicted. But then something happened that, while disappointing to those hoping for a brilliant celestial show, actually added another layer to our mystery. Atlas began to fragment, not all at once, but gradually, breaking into smaller and smaller pieces, its nucleus disintegrating before our watching eyes, or rather, before the watching eyes of telescopes around the world. This fragmentation, while it meant that Atlas would never become the bright comet many had hoped for, was actually a profound demonstration of the very process that might have created it in the first place. We were watching, in real time, the same kind of event that might have split the original parent comet into the fragments we see returning over the centuries. It was as if the universe was showing us, in compressed time, the deep history of these objects, the slow dissolution of ancient ice that has been circling our sun since before human civilization began. The fragmentation of comets isn't unusual. These objects, despite their appearance as solid bodies when seen from Earth, are actually quite fragile. They're often described as dirty snowballs, mixtures of ice and dust held together by weak forces, structured more like a pile of rubble than a solid rock. When they approach the sun, the heat causes the ice to sublimate, turning directly from solid to gas, and this process can create jets and geysers that put stress on the nucleus. Sometimes, the rotation of the comet spun up by these jets can cause it to fly apart. Sometimes, the tidal forces of the sun's gravity, pulling harder on the near side than the far side, can tear the nucleus apart, and sometimes we simply don't know what causes a comet to fragment. It happens, and we watch, and we learn. But in the case of Atlas, the fragmentation felt particularly poignant, because we might have been watching the last chapter in a story that began thousands of years ago. If Atlas was indeed a fragment of that ancient parent comet, then its dissolution in 2020 might have been the final act, the last time this particular piece of ancient ice would ever approach the sun. Or perhaps not. Perhaps the fragments of Atlas will continue on their orbit, smaller now, harder to see, but still following that same path, still carrying their cargo of ancient materials from the birth of our solar system. As we contemplate this cosmic mystery, it's worth pausing to consider what comets actually are and where they come from. These aren't just random chunks of ice wandering through space. They're messengers from the deep past preserved in the freezer of the outer solar system since the very beginning, when our sun was young and planets were still forming from the disk of gas and dust that surrounded our newborn star. Comets are composed of the same materials that built the planets, the same water that fills our oceans, the same organic molecules that would eventually lead to life. When we look at a comet, we're looking at our own origins, frozen in time and preserved in the darkness for billions of years. Most comets spend the vast majority of their existence in the outer reaches of the solar system, in regions so distant and cold that water ice is as solid and permanent as rock. There are two main reservoirs of comets: the Kuiper Belt, a disc-shaped region beyond Neptune where Pluto resides along with countless other icy bodies, and the Oort cloud, a vast spherical shell that surrounds our entire solar system at a distance so great that the sun would appear as just another star, perhaps a bit brighter than the others, but not dramatically so. The Oort cloud is thought to contain trillions of comets, all orbiting slowly in the darkness, taking millions of years to complete a single orbit around our distant sun. Occasionally, something disturbs one of these distant objects. Perhaps it's the gravitational influence of a passing star, or the tidal forces of the galaxy itself, or a collision with another comet. Whatever the cause, the comet's orbit changes, and it begins to fall toward the sun. This journey can take millions of years, a slow, patient drift through the darkness, accelerating gradually as the sun's gravity takes hold. As the comet approaches the inner solar system, somewhere around the orbit of Jupiter, it begins to warm. The ice starts to sublimate, creating a thin atmosphere called a coma around the nucleus. The solar wind and radiation pressure push this material away from the sun, creating the characteristic tail that makes comets such spectacular sights in our sky. The orbit of a comet tells us a great deal about its history. Long-period comets, like Atlas and the Great Comet of 1844, have orbits that take them far into the outer solar system, often to the Oort cloud itself. These orbits are measured not in years but in centuries or millennia. The Great Comet of 1844 had an orbital period estimated at around 600 years, though this is uncertain because we only observed it once, and orbital calculations from that era, while remarkably accurate given the tools available, weren't as precise as what we can achieve today. Atlas, before it fragmented, was on a similar orbit, though its period was calculated to be somewhat longer, perhaps 6,000 years or more. But here's where the mystery deepens. If Atlas and the Great Comet of 1844 are indeed fragments of the same parent body, then their orbits should be not just similar, but related in a very specific way. They should be like siblings who left home at different times but are following the same road. And that's exactly what astronomers found when they analysed the orbits carefully. The two comets share what's called similar orbital elements, the mathematical parameters that define their paths through space. They have similar inclinations, meaning they're tilted at nearly the same angle relative to the plane of the planets. They have similar eccentricities, meaning their orbits are stretched into similar elongated ellipses, and most tellingly, they pass through nearly the same point in space when they're closest to the Sun, what astronomers call the perihelion. This convergence of orbital elements is like finding two letters with different postmarks but the same return address. It suggests strongly that these two comets originated from the same source, that they're fragments of something larger that broke apart, each piece continuing on, essentially the same journey but arriving at different times. And if there are two fragments, might there be more? This is where our story expands from a simple connection between two comets to a broader mystery about a whole family of objects, all children of the same ancient parent, all following the same cosmic highway through our solar system. Indeed, as astronomers have looked more carefully at historical records and modern observations, they've found suggestions of other comets that might belong to this same family. There are faint comets observed in centuries past whose orbits, while not precisely determined due to limited observations, seem consistent with this same path. There are meteor streams, the trails of dust left behind by comets, that seem to follow similar orbits. It's as if we're discovering not just individual comets, but an entire genealogy written in ice and orbit, a family tree whose roots extend back thousands of years and whose branches are still revealing themselves to us. The idea of comet families isn't new to astronomy. We know of several groups of comets that share similar orbits and are thought to be fragments of larger parent bodies. The most famous might be the Kreutz sun grazers, a family of comets that pass extremely close to the Sun, so close that many of them don't survive the encounter. These comets are thought to be fragments of a single massive comet that broke apart perhaps 1,000 years ago, and we see members of this family regularly, sometimes several in a single year, as they make their final fatal plunge toward the Sun. But the family that includes Atlas and the Great Comet of 1844 is different. These aren't sun grazers. They don't pass particularly close to the Sun by cometary standards. Their parent must have fragmented for other reasons, perhaps due to a collision in the outer solar system, or perhaps simply due to the accumulated stresses of multiple passes by the Sun over thousands of years. Each pass would have heated the nucleus, caused some of the ice to sublimate, created tensions and cracks in the structure. Eventually, perhaps on a pass thousands of years ago that no human witnessed, the comet came apart, splitting into the fragments we're only now beginning to recognize as related. This raises a fascinating question. If we could trace these comets back far enough, if we could run the cosmic clock backward and undo the fragmentation, what would we find? How large was the original parent comet? When did it first fall from the Oort cloud toward the Sun? Was it witnessed by ancient civilizations? Did it inspire myths and legends that have come down to us in distorted form? Stories of dragons in the sky or celestial omens that we no longer connect to their astronomical origins? The Great Comet of 1844 appeared at a fascinating time in human history. The world was on the cusp of the modern era. The telegraph had just been invented, allowing news to travel faster than ever before. The railroad was beginning to transform transportation and commerce. Photography was in its infancy, and indeed, the Great Comet of 1844 was one of the first comets ever photographed, though the daguerreotype process of the time couldn't capture its full magnificence. This was also an era of great scientific advancement. Neptune would be discovered just 2 years later in 1846, using mathematical predictions based on gravitational perturbations. The foundations of modern astrophysics were being laid. The comet appeared in the sky at the end of 1844 and into early 1845, becoming visible to the naked eye in December and reaching its peak brightness in January. Contemporary accounts describe it as a magnificent sight, with a tail that stretched across a significant portion of the sky. In the southern hemisphere, where it was best visible, observers reported that it was bright enough to cast shadows. Ships' logs from vessels sailing the southern oceans contain numerous mentions of the comet, often with attempts to describe its beauty and magnitude. One particularly evocative account comes from the log of a British naval vessel sailing near Cape Horn. The comet tonight presents a most sublime spectacle, its tail sweeping across fully 30 degrees of sky, curved like a scimitar of light against the darkness. The men on watch stand transfixed, and even the officers, normally so composed, speak in hushed tones of this celestial visitor. It is as if the heavens themselves have unfurled a banner of light to guide our passage through these treacherous waters. In Tasmania, an amateur astronomer named Francis Abbott made detailed observations of the comet, carefully recording its position night after night, sketching its appearance, noting changes in the tail structure and brightness. His notebooks, preserved in a local historical society, provide some of the most detailed observational records we have of the comet. Abbott wrote, "The nucleus presents itself as a star of the first magnitude, surrounded by a nebulous envelope of considerable extent. The tail, which extends toward the northeast, shows a distinct curvature and appears to consist of multiple streamers, like ribbons of light twisted together by some celestial wind. These historical accounts are more than just curiosities. They provide us with data that modern astronomers can use to refine orbital calculations, to better understand the comet's behavior, and to strengthen or weaken the proposed connection to Atlas. When we combine these historical observations with modern computational methods, we can reconstruct the comet's path with surprising accuracy, and that reconstructed path aligns remarkably well with the orbit of Atlas. But the story of the Great Comet of 1844 extends beyond mere astronomical observation. Like all great comets throughout history, it became woven into the cultural fabric of its time. In Chile, where the comet was particularly well placed for observation, it was known as El Cometa de la Independencia, as it appeared during a time of political transformation and was seen by some as an omen of change. In southern Africa, various indigenous groups incorporated the comet into their oral traditions, with stories that speak of a great light that travelled across the sky, leaving seeds of light that would return in future generations. There's something deeply moving about reading these historical accounts while knowing about Atlas, about the possibility that we were seeing in 2020 a sibling of that same comet that inspired such wonder in 1844. It connects us across time in a way that few things can. The people who stood in fields and on ship decks in 1844, gazing up at that great comet, were looking at something that came from the same source as what we observed with our modern telescopes in 2020. We're united across the centuries by our shared wonder at these cosmic visitors, and yet our modern observations of Atlas revealed something that those 19th century observers couldn't have known. Through the powerful eyes of space telescopes and ground-based observatories, we watched as Atlas began to come apart. The Hubble Space Telescope captured images in April 2020 showing the comet's nucleus had fragmented into multiple pieces, each surrounded by its own small coma of sublimating gas and dust. It was like watching a dandelion seed head slowly dispersing in a gentle breeze, except this was happening on a cosmic scale, with chunks of ancient ice the size of buildings or city blocks drifting apart in the darkness millions of miles from Earth. This fragmentation was both a disappointment and a revelation. A disappointment because it meant Atlas would never achieve the brightness that early predictions had suggested. Instead of becoming a naked-eye spectacle visible to everyone, it remained a target for telescopes and binoculars, a subtle ghost that required patience and dark skies to observe. But it was also a revelation because it showed us directly the process that might have created Atlas in the first place. We were witnessing the same kind of fragmentation event that might have split the original parent comet into the pieces we're now tracking across the centuries. The fragmentation of Atlas was studied intensively by astronomers around the world, Different telescopes captured the event at different wavelengths of light, revealing different aspects of the process. Infrared observations showed the heat signature of the fragments. Ultraviolet observations reveal the gases being released. And visible light images track the physical separation of the pieces. It was like watching a slow-motion explosion, except instead of violence and chaos, there was an almost serene quality to the comet's dissolution, a gentle drifting apart that spoke of the fundamental fragility of these ancient objects. One of the most poignant aspects of watching Atlas fragment was the realization that we were possibly witnessing the end of something that had existed since before the Earth itself was fully formed. The ice and dust that composed Atlas had been locked together in the deep freeze of the outer solar system for billions of years. It had survived the birth of the planets, the evolution of life on Earth, the rise and fall of countless species, the entire history of human civilization. And then, in the span of a few weeks in 2020, it came apart, releasing its ancient materials into space where they would drift as individual particles, perhaps eventually to be swept up by planets or blown out of the solar system entirely by the pressure of sunlight. But even as Atlas was fragmenting, it was teaching us. The way it came apart, the rate at which the fragments separated, the amount of dust and gas released, all of these observations provide clues about the comet's structure and composition. Comets, it turns out, aren't uniform objects. They're more like loosely bound collections of smaller pieces, what astronomers call rubble piles, held together by weak forces and their own minimal gravity. When something disturbs this delicate balance, whether it's solar heating, rotational forces, or tidal stresses, the comet can come apart relatively easily. This fragile structure might seem like a weakness, but it's actually key to understanding how comets can survive for billions of years in the outer solar system, and yet come apart so readily when they approach the Sun. In the cold depths of space, where temperatures hover just a few degrees above absolute zero, the ice that makes up much of a comet's mass is as solid and strong as rock. But as the comet approaches the Sun and warms up, that ice begins to sublimate, turning directly from solid to gas, and the forces that held the comet together weaken. It's like a snowball that's been in the freezer for years, suddenly being placed in warm sunlight. What seemed solid and permanent begins to reveal its temporary nature. The connection between Atlas and the Great Comet of 1844, if real, tells us that this process of fragmentation and dissolution has been going on for a very long time. The parent comet, whatever it was, has been slowly coming apart over centuries or millennia, each fragment making its own journey around the Sun, each one potentially fragmenting further. It's a cascade of dissolution, a family tree written in ice and dust, with each generation smaller and more numerous than the last. This brings us to a profound realization about the nature of comets, and by extension, about the solar system itself. Nothing is permanent. Everything is in a state of slow transformation. The comets that grace our skies are temporary phenomena on cosmic timescales, brilliant for a moment and then gone, their materials dispersed to become part of something else. The water in Earth's oceans might once have been locked in comets like Atlas. The organic molecules that form the building blocks of life might have been delivered by similar ancient visitors. We are, in a very real sense, made of comet stuff, assembled from materials that once drifted in the outer darkness and were brought to the inner solar system by these fragile messengers. As we continue our journey into this cosmic mystery, let's travel back even further, beyond the Great Comet of 1844, beyond any human historical record, to imagine the original parent comet in its pristine state. Picture, if you will, an object perhaps tens of miles across, a small mountain of ice and dust held together by weak gravity and frozen solid in the unimaginable cold of the Oort cloud. This object has been orbiting slowly in the darkness for billions of years, so far from the Sun that our star appears no brighter than other stars in the sky. It's a patient, eternal orbit, unchanging and undisturbed. But then something happens. Perhaps a star passes relatively close to our solar system, still light years away, but close enough that its gravity creates a subtle perturbation in the Oort cloud. Or perhaps it's the accumulated effect of the galaxy's tidal forces, the gentle pull of billions of distant stars acting over millions of years. Whatever the cause, our protocomet's orbit is nudged, changed just slightly, but enough to send it falling toward the Sun. This journey will take millions of years, a slow drift through the darkness, gradually accelerating as the Sun's gravity takes hold. As the comet falls inward, it passes through regions of space that no human eyes have ever seen directly. It crosses the heliopause, the boundary where the solar wind meets the interstellar medium. It passes through the scattered disk, a region of icy bodies beyond Neptune. It crosses the orbit of Neptune itself, then Uranus, then Saturn. With each passing milestone it accelerates, its orbit bending more sharply as the Sun's gravity grows stronger. And somewhere along this journey, perhaps near Jupiter's orbit, it begins to warm. The ice that has been solid for billions of years begins to sublimate. The comet develops a coma, then a tail. It has become the spectacular object that humans will one day observe and wonder at. But this first pass by the Sun is traumatic for our ancient comet. The heating is uneven, creating stresses in the nucleus. Jets of gas burst from weak points, spinning the comet faster. The tidal forces of the Sun's gravity pull at its structure. Perhaps on this first pass, perhaps on a subsequent one, the comet begins to fragment. Not all at once, but gradually cracks propagating through the nucleus, pieces beginning to separate. What was once a single object becomes two, then perhaps more. Each fragment continues on essentially the same orbit, but they drift apart slowly, spreading out along the orbital path like a string of pearls. This process of fragmentation might have happened thousands of years ago, perhaps even tens of thousands of years ago. The fragments would have continued to orbit, each one returning to the inner solar system on its own schedule. Some might have been seen by ancient civilizations, inspiring myths and legends. Others might have passed unseen, too faint or poorly placed for observation. The Great Comet of 1844 was one of these fragments, making its appearance at a time when humanity was just beginning to understand the true nature of comets. And Atlas was another, arriving in our skies at a moment when we had the technology to study it in unprecedented detail and perhaps recognize its connection to that earlier visitor. The idea that we might be seeing the return of fragments from an ancient comet raises fascinating questions about human history and mythology. Throughout recorded history, comets have been seen as omens, portents, messengers from the gods. They've been blamed for plagues and credited with victories. They've marked the deaths of kings and the births of religions. If the parent comet of Atlas and the Great Comet of 1844 has been fragmenting for thousands of years, might some of these fragments have been the comets that changed history? Consider, for example, the Great Comet of 1680, one of the brightest comets ever recorded, visible even in daylight. Its orbit, while not identical to that of Atlas and the 1844 comet, shares some similarities. Could it be another fragment of the same parent? Its orbit evolved slightly differently due to gravitational perturbations. Or the comet of 1106, recorded by astronomers in Europe, Asia, and the Middle East, described as being visible during the day for weeks. The historical records aren't precise enough to calculate an exact orbit, but the descriptions are tantalizing. We must be careful here not to see connections where none exist. The human mind is excellent at finding patterns, even in random data. But the possibility that some of history's great comets might be related, might be fragments of the same ancient parent, adds a layer of continuity to human experience that's both humbling and inspiring. It suggests that across cultures and centuries, humans have been witnessing the slow dissolution of the same cosmic object, each generation seeing a different piece of the puzzle without realizing they were all looking at parts of the same picture. The fragmentation of comets also creates smaller debris that we experience in a different way, as meteor showers. When Earth passes through the trail of dust left behind by a comet, these tiny particles enter our atmosphere and burn up, creating the streaks of light we call meteors or shooting stars. Many of our annual meteor showers are associated with known comets. The Perseids come from Comet Swift-Tuttle, the Leonids from Comet Tempel-Tuttle, the Orionids and Eta Aquarids from the famous Halley's Comet. If Atlas and the Great Comet of 1844 are indeed fragments of the same parent, then there should be a trail of debris along their orbit, and Earth might pass through this trail at some point in its annual journey around the Sun. Astronomers have looked for such a meteor shower, and while no strong shower has been definitively linked to this comet family, there are some weak showers whose orbits are suggestively similar. It's possible that the debris trail is too dispersed, or that Earth's orbit doesn't quite intersect it, or that we simply haven't recognized the connection yet. Imagine, though, the possibility that some of the shooting stars you might see on a clear night could be tiny fragments of the same parent comet that gave us Atlas and the Great Comet of 1844. These would be ancient particles, older than life on Earth, that have been circling the Sun for millennia, waiting for their brief moment of glory as they streak across our sky. Each meteor would be a tiny messenger from the deep past, a spark of light connecting us to the formation of our solar system. The study of comet families like the one that might include Atlas gives us insights into the larger population of comets in our solar system. If comets fragment regularly, then the number of comets should be increasing over time, with each parent comet spawning multiple fragments. But we also know that comets have finite lifetimes. Each pass by the Sun removes some material, and eventually a comet will either completely sublimate away or become a dead nucleus, a dark rock with all its ice gone. This balance between creation through fragmentation and destruction through sublimation maintains a dynamic population of comets, a constant renewal and recycling of ancient materials. The Oort cloud, that vast reservoir of comets at the edge of our solar system, is thought to contain trillions of these objects. If even a tiny fraction of them are perturbed into orbits that bring them into the inner solar system, and if many of them fragment to create families of comets, then the sky should be full of these visitors. And indeed it is, though most are too faint for us to see without telescopes. Professional and amateur astronomers discover dozens of new comets each year, most of them faint objects that never become visible to the naked eye. Each one is a messenger from the deep past, a fragment of the primordial material from which our solar system formed. As we think about Atlas and its possible connection to the Great Comet of 1844, we're really thinking about time on scales that dwarf human experience. The orbital period of these comets, thousands of years, means that they've completed only a handful of orbits since human civilization began. The parent comet, if it came from the Oort cloud, might have been orbiting there since before the Earth fully formed, since before life began, since before the Sun had settled into its stable middle age. The ice in these comets is older than the oldest rocks on Earth, older than the Moon, nearly as old as the Sun itself. This deep time perspective can be both humbling and comforting. Our daily concerns, our human dramas, our civilizations and their rises and falls all take place in what is, from a cosmic perspective, the briefest of moments. The comets don't care about our politics, our wars, our achievements or failures. They simply continue their ancient orbits, following the laws of physics that have governed their motion since the beginning. There's a kind of peace in this, a reminder that the universe operates on scales and timelines that make our human troubles seem temporary and small. Yet at the same time, we are the only beings we know of who can appreciate this cosmic perspective. We are the universe becoming aware of itself, as Carl Sagan once said. When we observe a comet, when we calculate its orbit, when we recognize its connection to another comet seen centuries ago, we're doing something that, as far as we know, has never been done before in the history of the universe. We're bearing witness to the cosmos, understanding it, finding meaning and beauty in the dance of ice and light across the darkness. The story of Atlas is still being written. Even though the main nucleus fragmented in 2020, the pieces continue on their orbit. Some of them might still be large enough to survive another pass by the Sun, returning in a few thousand years as faint comets in their own right. The dust and gas released by Atlas is spreading out along its orbit, adding to the trail of debris that future Earth might pass through. And somewhere out there, perhaps, are other fragments of the original parent comet, chunks of ice that haven't yet made their appearance in our skies, but are slowly falling toward the Sun, destined to arrive in decades or centuries to come. Modern astronomy has given us tools to search for these family members. Large survey telescopes scan the sky every night, cataloguing moving objects, building up a census of the solar system's small bodies. Machine learning algorithms sift through this data, looking for patterns, identifying objects that might be related. Space missions to comets, like the European Space Agency's Rosetta mission to Comet 67P, Churyumov-Gerasimenko, have given us close-up views of cometary nuclei, showing us their structure and composition in unprecedented detail. Each piece of data adds to our understanding, helping us piece together the complex history of these ancient objects. The connection between Atlas and the Great Comet of 1844, while strongly suggested by their similar orbits, remains a hypothesis rather than a proven fact. To confirm it definitively, we would need to analyze the composition of both comets, looking for chemical signatures that would prove they came from the same parent body. For the Great Comet of 1844, we have only historical observations, no physical samples or detailed spectroscopic data. For Atlas, we have modern observations including spectroscopy, but the comet's fragmentation means we'll never be able to study it as closely as we might have liked. This uncertainty is part of the beauty of the story. Science is not about having all the answers, but about asking the right questions, about following clues and building hypotheses, about remaining open to wonder while maintaining rigorous standards of evidence. The possible connection between Atlas and the Great Comet of 1844 is a perfect example of this process. We have tantalizing hints, suggestive evidence, reasonable hypotheses, but not absolute proof. And that's okay. The mystery remains, inviting future observations, future discoveries, future moments of wonder. As you drift towards sleep tonight, perhaps you can imagine yourself floating in space, watching these ancient travelers on their long journeys around the Sun. See them not as isolated objects, but as part of a vast, interconnected system, a family of fragments spreading out through space and time, each one carrying a piece of the same ancient story. Think of the people in 1844 who looked up at their great comet with wonder, not knowing that people in 2020 would be looking at its sibling. Think of future generations who might see other fragments, adding their observations to this multi-century chronicle. The universe is full of these connections, these patterns that span scales of space and time far beyond human experience. Comets are just one example, but they're a particularly poetic one. They appear in our skies as sudden visitors, bright and beautiful, then fade away, leaving only memories and measurements. But they're not really visitors at all. They're part of our solar system's extended family, distant relatives who come to visit occasionally, reminding us of our shared origins in the cloud of gas and dust that gave birth to the Sun and all its planets. The possibility that Atlas and the Great Comet of 1844 share a common origin leads us deeper into one of the most beautiful mysteries in astronomy, the phenomenon of comet families and the slow, patient fragmentation of these ancient travelers. When we speak of a parent comet, we're imagining something magnificent, something that would have dwarfed both Atlas and the Great Comet of 1844, a primordial mountain of ice perhaps 50 or even 100 kilometers across, a world unto itself, drifting through the outer darkness for billions of years before beginning its long fall toward the Sun. This parent, this ancestor of the comets we've observed, would have been a repository of the solar system's earliest materials, water ice formed in the cold depths of space, dust grains that predate the Earth itself, organic molecules that might hold clues to the origins of life, all locked together in a matrix of frozen time. To understand the ghost of this parent comet, we need to think about what happens when such a massive object approaches the Sun for the first time. Picture this ancient Voyager, pristine and unchanged since the solar system's formation, beginning to feel the Sun's warmth as it crosses the orbit of Jupiter. For the first time in billions of years, the ice begins to sublimate, turning directly from solid to gas, creating jets and fountains that burst from the surface. These jets don't emerge uniformly. They concentrate at weak points, at boundaries between different types of ice, at places where the structure is already stressed. And as these jets fire, they act like tiny rockets, beginning to spin the comet, creating forces that the fragile structure was never meant to withstand. The tidal forces add another layer of stress. The Sun's gravity pulls harder on the near side of the comet than the far side, creating a stretching force that tries to pull the comet apart. For a small comet a few kilometers across, these forces might be manageable, but for a massive parent comet tens of kilometers across, the stresses can be enormous. Cracks begin to propagate through the nucleus, following lines of weakness, boundaries between the original cometesimals that came together billions of years ago to form this object. The comet holds together through this first passage perhaps, but it's been weakened, fractured, primed for future dissolution. On subsequent orbits, the process continues. Each pass by the Sun removes more material, deepens the cracks, increases the spin rate. And then, perhaps on the third passage, or the fifth, or the 10th, the forces finally overcome the weak gravity holding the comet together. The fragmentation might not be dramatic at first. Perhaps a small piece carves off, like an iceberg separating from a glacier. This piece continues on essentially the same orbit as the parent, but it begins to drift away slowly, the two objects becoming separate comets that will return to the inner solar system at slightly different times. This process of fragmentation is not unique to our hypothetical parent comet. We've observed it happening with other comets throughout history. Comet Shoemaker-Levy 9 provided a spectacular example in the 1990s when it was torn apart by Jupiter's gravity, and the fragments crashed into the giant planet in 1994, leaving dark scars in Jupiter's atmosphere that persisted for months. Comet 73P Schwarzmann-Wachmann fragmented before our eyes in 1995 and continued to break apart in subsequent returns. Comet Linear disintegrated completely in 2000, going from a normal comet to a cloud of debris in a matter of weeks. But the fragmentation we're discussing with our parent comet would have been different, slower, more gradual. Instead of a sudden catastrophic breakup, we're imagining a process that played out over centuries or millennia, with pieces separating gradually, each one continuing to orbit but slowly spreading out along the orbital path. This is why Atlas and the Great Comet of 1844 could arrive at different times despite sharing the same origin. They're like runners who started the race together but now spread out along the track, each moving at slightly different speeds, each destined to cross the finish line at a different time. The mathematics of orbital mechanics tells us that even small differences in velocity at the time of fragmentation can lead to significant differences in orbital period. A fragment that receives a tiny boost of velocity from the fragmentation event might have an orbital period hundreds of years longer than its sibling. A fragment that loses a bit of velocity might return centuries sooner. Over thousands of years, these differences accumulate, spreading the fragments out along the orbit until they arrive at completely different times, their common origin hidden unless we look carefully at the shape and orientation of their orbits. This spreading of fragments along an orbit creates what astronomers call a comet stream or comet family. The Kreutz sun grazers are the most famous example, with dozens of known members all following nearly identical orbits that take them extremely close to the Sun. But there are other families too, less dramatic but equally fascinating. The Jupiter family comets, for instance, are a large group of comets with orbits that have been shaped by Jupiter's gravity. While these aren't fragments of a single parent, They demonstrate how orbital dynamics can create families of objects with related characteristics. Our proposed family, the one that includes Atlas and the Great Comet of 1844, would be what's called a long-period comet family. These are rarer and harder to identify than short-period families because the long intervals between returns mean we have fewer observations to work with. A comet with a 6,000-year period has completed only one orbit since the construction of the pyramids. Human civilization hasn't existed long enough to see these comets return even once, so we're trying to piece together family relationships based on single observations separated by centuries. The evidence for the connection between Atlas and the Great Comet of 1844 comes primarily from their orbital elements. When astronomers calculate an orbit, they determine 6 numbers that completely describe the path. The semi-major axis, which determines the size of the orbit, the eccentricity, which determines how elongated it is, the inclination, the tilt relative to Earth's orbit, the longitude of the ascending node, where the orbit crosses Earth's orbital plane, the argument of perihelion, the orientation of the orbit in space, and the time of perihelion passage when the object is closest to the Sun. For Atlas and the Great Comet of 1844, 5 of these 6 numbers are remarkably similar. Only the time of perihelion passage differs, which is exactly what we'd expect for fragments that separated long ago. But orbital similarity alone isn't absolute proof of a common origin. Comets can have similar orbits by coincidence, especially long-period comets coming from the same general region of the Oort cloud. To strengthen the case for a family connection, astronomers look for additional evidence. One piece of supporting evidence comes from the fragmentation of Atlas itself. If Atlas was already a fragment of a larger parent, it might be more prone to further fragmentation, having inherited structural weaknesses from the original breakup. The fact that Atlas fragmented as it approached the Sun in 2020 is consistent with this idea, though it's not definitive proof. Another line of evidence comes from studying the composition of the comets. Each comet has a unique chemical fingerprint, determined by the ratios of different ices, the types of dust grains, the presence of various organic molecules. If Atlas and the Great Comet of 1844 are truly siblings, they should have very similar compositions. For Atlas, we have modern spectroscopic observations that tell us about its composition. We can detect water ice, of course, but also carbon monoxide, carbon dioxide, methanol, and various other molecules. The ratios of these different components create a chemical signature as unique as a fingerprint. For the Great Comet of 1844, unfortunately, we don't have such detailed data. Spectroscopy was in its infancy in 1844, and while some observers attempted to study the comet's light through prisms, their observations were crude by modern standards. We know the comet was described as having a yellowish colour, which might indicate a high dust content, and some observers noted a greenish tinge to the coma, which typically comes from diatomic carbon molecules. But these qualitative observations can't give us the precise chemical ratios we'd need for a definitive comparison. This is one of the frustrations and fascinations of studying comet families. We're trying to connect objects across centuries using modern techniques to analyze recent comets, while relying on historical records for their supposed siblings. It's like trying to prove a family relationship when we have DNA from one person, but only a painted portrait of the other. The resemblance might be striking, but we can't be absolutely certain. Yet even without absolute proof, the hypothesis that Atlas and the Great Comet of 1844 share a common parent is compelling enough that astronomers take it seriously. It fits into a larger pattern we're beginning to understand about how comets evolve and fragment over time, and it raises intriguing questions about what other fragments might be out there, still approaching the Sun on their long journeys from the outer darkness. If the parent comet fragmented into Atlas and the Great Comet of 1844, it almost certainly produced other fragments as well. Fragmentation events rarely produce just 2 pieces. They typically create multiple fragments of various sizes. Some of these might be large enough to become bright comets in their own right. Others might be smaller, appearing as faint comets detectable only with telescopes. And the smallest fragments would become part of a meteoroid stream, particles of dust and ice that might one day enter Earth's atmosphere as meteors. The search for additional family members is ongoing. Astronomers regularly review historical comet observations, looking for objects whose orbits might match the Atlas 1844 family. They also monitor current comet discoveries, checking each new object's orbit against known families. It's painstaking work, complicated by the fact that orbits evolve over time due to gravitational perturbations from the planets. A comet that passed close to Jupiter centuries ago might have had its orbit altered enough that the family connection is no longer obvious. There are several historical comets that are candidates for membership in this family, though none with orbits as closely matched as Atlas and the Great Comet of 1844. The comet of 1500, observed across Europe and Asia, followed a path that might be consistent with this family, though the observations aren't precise enough to be certain. The comet of 539 AD, recorded in Chinese astronomical texts, is another possibility. These ancient observations are tantalizing but frustratingly imprecise. The observers of the time were more interested in the astrological significance of comets than in their precise positions, and they lacked the mathematical framework to calculate orbits. Even more intriguing is the possibility that some of the fragments haven't been observed yet. If the parent comet fragmented thousands of years ago, and if the fragments spread out along the orbit with different periods, then some pieces might still be approaching, destined to arrive in our skies in the coming decades or centuries. There could be a bright comet, a sibling of Atlas and the Great Comet of 1844, already falling toward the Sun but still too far away for our telescopes to detect. It might arrive in 50 years, or 100, or 500, carrying with it another piece of the puzzle, another chapter in this multimillennial story. The idea that we might be awaiting future fragments adds a temporal dimension to this cosmic mystery that's both exciting and humbling. We're not just studying the past, we're anticipating the future. Every new comet discovered might be a member of this family. Every faint smudge detected by survey telescopes might be another fragment of that ancient parent, returning home after thousands of years in the darkness. This brings us to a profound realization about the nature of scientific discovery. We often think of science as uncovering fixed truths about the universe, but in cases like this, we're participants in an ongoing story. The astronomers who observed the Great Comet of 1844 couldn't have known they were seeing part of a family. The observers of Atlas in 2020 initially had no idea it might be related to that 19th century spectacle. Only by combining observations across centuries, by building on the work of previous generations, can we begin to see the larger pattern. And future astronomers, with tools and techniques we can't imagine, might look back at our observations and see connections we've missed, patterns we couldn't recognize. The fragmentation of the parent comet, whenever it occurred, would have been a slow-motion catastrophe of incredible scale. Imagine a mountain of ice, larger than Mount Everest, slowly coming apart in the vacuum of space. There would be no sound, of course, no dramatic explosion, just a gradual separation, pieces drifting apart at walking speed, each piece continuing to sublimate, creating its own coma and tail. From Earth, if anyone had been watching with sufficient telescopes, it might have looked like a single comet becoming 2, then 3, then more, a celestial cell division playing out over weeks or months. The forces involved in such a fragmentation are surprisingly gentle by earthly standards. The gravity holding a comet together is weak. You could probably jump off a small comet and never come back. The escape velocity from a 10-kilometer comet is only about 10 meters per second, roughly the speed of a sprinting human. So when a comet fragments, the pieces don't fly apart dramatically. They separate gently, almost lazily, drifting apart like boats whose moorings have been cut. This gentle separation means that the fragments initially stay close together, traveling in a group like a cosmic convoy. But over time, Small differences in their orbits caused them to spread out. The fragments that received a slight forward push during the breakup move into slightly larger orbits with longer periods. Those that received a backward push fall into slightly smaller orbits with shorter periods. After one orbit, the differences might be measured in months. After 10 orbits, the separation might be centuries. After 100 orbits, the fragments might be spread around the entire orbit, arriving at completely different times, their common origin forgotten. The parent comet itself was probably a product of the early solar system, formed in the protoplanetary disk that surrounded the young sun 4.6 billion years ago. In those early days, the solar system was a much more chaotic place. Planets were still forming, migrating, colliding. The region where the giant planets now orbit was full of icy planetesimals, the building blocks of planets that never quite came together. Some of these planetesimals were ejected from the solar system entirely by gravitational encounters with the growing planets. Others were thrown into the distant Oort cloud, where they have been waiting ever since, preserved in the deep freeze of interstellar space. Our parent comet would have been one of these exiled objects, thrown into the Oort cloud billions of years ago and orbiting there quietly until something, perhaps a passing star or the tidal forces of the galaxy itself, sent it falling back toward the sun. That initial perturbation might have happened millions of years ago, beginning a journey that would eventually lead to the fragmentation event and the creation of the comet family we're now trying to understand. The Oort cloud itself is one of the most mysterious regions of our solar system. We've never seen it directly. It's too far away, and the objects in it are too small and dark. We infer its existence from the orbits of long-period comets, which seem to come from all directions, suggesting a spherical cloud of objects surrounding the solar system. The Oort cloud is thought to extend from about 2,000 astronomical units, AU, from the Sun to perhaps 100,000 AU or more. For comparison, Neptune orbits at about 30 AU, and the Voyager 1 spacecraft, launched in 1977, and now the most distant human-made object, is only about 160 AU from the Sun. The number of objects in the Oort cloud is staggering. Estimates suggest there might be trillions of comets out there, ranging from tiny chunks of ice to objects hundreds of kilometers across. The total mass might be several times the mass of Earth, all in the form of these frozen remnants from the solar system's formation. It's a vast reservoir of ancient material, a library of the early solar system written in ice and dust, waiting to be read. When we see a comet like Atlas or the Great Comet of 1844, we're seeing an ambassador from this distant realm, a messenger that's travelled for millions of years to bring us information about the outer reaches of our solar system and the time of its formation. The fact that these two comets might be fragments of the same parent adds another layer to the message. They're telling us not just about the Oort cloud and the early solar system, but about the processes of fragmentation and evolution that comets undergo, about the complex dynamics that govern these ancient objects. The study of comet families also has practical implications. If we can identify families of comets and predict when fragments might arrive, we can prepare for their observation. We can alert amateur astronomers to watch for new family members. We can schedule telescope time to study them. And in the unlikely but not impossible event that a large fragment is on a collision course with Earth, advance warning would be crucial for any mitigation efforts. But beyond the practical considerations, there's something deeply poetic about comet families. They're celestial genealogies written across the sky, family trees whose branches are separated by centuries and whose roots extend back to the birth of the solar system. When we recognize these relationships, when we connect comets observed centuries apart as siblings from the same parent, we're reading a story that transcends human timescales, a narrative that connects us to the deep history of our cosmic neighborhood. The fragmentation that created Atlas and the Great Comet of 1844 from their parent wasn't an ending but a transformation. The parent comet didn't die, it multiplied, became many from one, spread its substance across multiple objects that would each have their own journey, their own moment in the sun, their own opportunity to be witnessed and wondered at by whatever eyes might be watching when they arrived. In a sense, the fragmentation gave the parent comet a kind of immortality, or at least a greatly extended existence, allowing it to visit the inner solar system not once, but many times, in many forms, across many centuries. And what of Atlas itself, now that it too is fragmented? The pieces continue on their orbit, smaller now, fainter, but still following essentially the same path. Some of these fragments might be large enough to survive another passage by the Sun, returning in a few thousand years as faint comets in their own right. They would be the grandchildren of the original parent, carrying forward the family legacy into the distant future. Other fragments are probably too small to survive, destined to completely sublimate away on their next approach to the Sun, their materials dispersed into interplanetary space. The smallest fragments, the dust and tiny particles released by Atlas's disintegration, are spreading out along the orbit, creating a meteor stream that might one day intersect Earth's path. If that happens, we might see a new meteor shower, faint perhaps, but directly connected to Atlas, and, through it, to the great comet of 1844 and their ancient parent. Each meteor would be a tiny piece of that original comet, a spark of light connecting us across thousands of years to that primordial fragmentation event. This is the way of comets. They come and go, they fragment and disperse. They create families that spread across centuries. They're temporary phenomena on cosmic timescales, but their effects ripple outward through time. The water they carry might end up in planetary atmospheres or oceans. The organic molecules they contain might seed the chemistry that leads to life. The dust they release might become part of new planets around distant stars. Nothing is permanent, but nothing is truly lost either. It all continues in different forms, following different paths, but still connected to its origins in the cold depths of space. As we contemplate this ghost of a parent comet, we're really contemplating the nature of change and continuity in the cosmos. The parent comet no longer exists as a single object, but it persists in its fragments, in Atlas and the great comet of 1844, and perhaps in other pieces still unknown to us. It persists in the meteoroid stream spreading along its orbit. It persists in the water vapor and dust that its fragments have released into the solar system. And it persists in our knowledge and wonder, in the human understanding that connects these disparate observations into a coherent story. The promise that Atlas seemed to offer in early 2020 was the promise of spectacle, of a bright comet that would grace our skies and provide a moment of cosmic beauty in troubled times. As the comet brightened through March of that year, hopes rose that it might become visible to the naked eye, perhaps even spectacular, a celestial event that would unite humanity in wonder as we all looked up at the same cosmic visitor. Predictions varied, but some suggested Atlas might become as bright as Venus, visible even from light-polluted cities, with a tail stretching across a significant portion of the sky. These predictions were based on the comet's initial rate of brightening and comparisons with other comets that had followed similar trajectories. Comets are notoriously unpredictable, their brightness depending on factors that are difficult to model: the size of the nucleus, the rate of sublimation, the composition of the ice, the presence of particularly volatile components that might suddenly activate as the comet warms. But the early signs for Atlas were promising. It was brightening faster than expected, suggesting either a large nucleus or particularly active sublimation, or both. The excitement wasn't just among professional astronomers. Amateur astronomers around the world turned their telescopes toward Atlas, tracking its progress, measuring its brightness, photographing its developing tail. Online forums buzzed with observations and predictions. Star charts were shared showing where to find the comet. People who had never observed a comet before prepared to try, hoping to witness something special, something that might not come again in their lifetimes. There was something particularly poignant about this excitement in the context of early 2020. As the world was entering a period of isolation and uncertainty, As daily life was being disrupted in unprecedented ways, the approach of a potentially bright comet felt like a gift from the universe, a reminder that beauty and wonder continued regardless of earthly troubles. People spoke of watching the comet as a family activity, something that could be done while maintaining social distance, a way to connect with something larger than our immediate concerns. But even as excitement built, experienced comet observers counseled caution. They'd seen this before, a comet that seemed destined for greatness suddenly fading, falling apart, failing to live up to its promise. Comets are fragile things, and the very processes that make them bright also destroy them. The closer they get to the sun, the more spectacular they can become, but also the more stress they experience. It's a cosmic catch-22. To be brilliant, a comet must risk destruction. The first signs that Atlas might not fulfill its promise came in early April 2020. The comet's rate of brightening began to slow, then stopped altogether. Instead of continuing to brighten as it approached the sun, Atlas seemed to stall, its magnitude plateauing when it should have been increasing. Amateur astronomers reported that the comet's appearance was changing, its once concentrated coma becoming more diffuse, elongated, irregular. Professional astronomers turned larger telescopes toward the comet and confirmed what many feared. Atlas was beginning to fragment. The fragmentation wasn't immediately catastrophic. At first, the nucleus seemed to elongate, as if stretching under some invisible force. Then observers began to report multiple condensations within the coma, distinct bright points where there should have been only one. The Hubble Space Telescope was tasked to observe Atlas on April 20th and April 23rd, 2020, and the images it returned were definitive. The comet's nucleus had broken into multiple pieces, at least 4 major fragments and numerous smaller ones, all surrounded by their own small comae, all drifting slowly apart. For those hoping for a spectacular naked-eye comet, this was disappointing news. A fragmenting comet might briefly brighten as fresh ice is exposed, but it typically then fades rapidly as the smaller pieces lack the mass to sustain significant sublimation. The fragments spread out, the coma becomes diffuse, and what might have been a brilliant spectacle becomes a faint, extended glow, barely visible even in telescopes. Atlas would not be the comet of the century, would not provide the celestial show that many had hoped for. But from a scientific perspective, the fragmentation of Atlas was fascinating. Here was an opportunity to watch a comet come apart in real time, to study the process of fragmentation with modern instruments, to learn about the structure and composition of cometary nuclei. Every major telescope that could observe Atlas was turned toward it. Spectroscopic observations revealed the composition of the gases being released. Infrared observations showed the thermal emission from the fragments. Radio telescopes detected molecules like hydrogen cyanide and methanol. Each observation added to our understanding of what Atlas was made of and how it was coming apart. The fragmentation also provided evidence for the connection between Atlas and the Great Comet of 1844. If both comets were fragments of a larger parent, then Atlas might have inherited structural weaknesses from that original fragmentation event. The fact that it came apart so readily, even though it wasn't passing particularly close to the Sun by cometary standards, suggested that it was already fragile, already fractured, already primed to fragment further. It was like watching a piece of ancient pottery that had been glued back together fall apart again along the old cracks. The way Atlas fragmented was also instructive. It didn't explode or shatter suddenly. Instead, it seemed to gently separate, the pieces drifting apart slowly, each continuing to sublimate at its own rate. This gentle fragmentation is consistent with a nucleus that was already loosely bound, perhaps never fully consolidated after the original fragmentation event that created it. It suggests that Atlas was less like a solid chunk of ice, and more like a rubble pile, a collection of smaller pieces held together by weak forces that were easily overcome by the stresses of solar approach. As April turned to May in 2020, Atlas continued to fade. the fragments spread out along the orbit, becoming fainter and more diffuse. By late May, what had once been a promising comet was barely visible even in large telescopes. A ghostly glow spread across a significant area of sky. By June, Atlas had faded below the detection limit of most amateur telescopes. The comet that had promised so much had delivered instead a lesson in the fragility of these ancient objects and the unpredictability of their behavior. Yet even in its dissolution, Atlas was teaching us. The fragmentation event had exposed fresh ice that had been locked in the interior of the nucleus, ice that might have been pristine since the comet's formation billions of years ago. The spectroscopic signatures of this newly exposed material provided clues about the comet's composition and history. The way the fragments separated told us about the structure of the nucleus and the forces that held it together. Every observation, even of the fading fragments, added to our understanding. The disappointment over Atlas's failure to become a great comet was tempered by the appearance of another comet that did fulfill its promise. Comet Neowise, discovered in March 2020, just days before Atlas began to fragment, survived its close approach to the Sun and became a beautiful naked-eye comet in July 2020. For a few weeks, Neowise graced the evening sky, visible to millions of people around the world, providing the celestial spectacle that Atlas had promised but failed to deliver. It was as if the universe, having disappointed us with one comet, offered another as compensation. The contrast between Atlas and Neowise is instructive. Both comets came from the outer solar system, both approached the Sun on long-period orbits, both had the potential to become bright. But Neowise's nucleus held together while Atlas's came apart. This difference might come down to composition, structure, size, or history. Neowise might have been a more consolidated nucleus, or it might have been making its first approach to the Sun, still fresh and strong. Atlas, possibly a fragment of an already fragmented parent, might have been structurally compromised from the start. The story of Atlas's fragmentation also connects to larger questions about the delivery of water and organic molecules to Earth. Comets have long been proposed as one source of Earth's water, and possibly even the organic molecules that led to life. But if comets fragment readily, if they come apart under the stresses of solar approach, then their ability to deliver materials to planets becomes more complex. Instead of single large impacts delivering vast amounts of water, we might need to think about countless smaller impacts, a gentle rain of cometary fragments over millions of years. The fragments of Atlas, now drifting apart in space, will continue their journey around the Sun. Some might be large enough to survive another perihelion passage, returning as faint comets in a few thousand years. Others will probably sublimate completely on their next approach, their materials dispersed into interplanetary space. The smallest fragments, dust particles and tiny ice grains, are spreading out along the orbit, creating a debris trail that Earth might one day pass through. If Earth does encounter this debris trail, we might see meteors that are directly connected to Atlas. These wouldn't be spectacular fireballs, but rather faint streaks of light, visible only from dark sites on clear nights. But each one would be a piece of Atlas, and through Atlas, a piece of the Great Comet of 1844, and through that, a piece of the ancient parent comet. Each meteor would be a messenger across time, a spark of light connecting us to the deep history of the solar system. The failure of Atlas to become a great comet also reminds us of the role of chance in astronomical events. Had Atlas held together just a few more weeks, had its nucleus been slightly stronger, or its approach to the Sun slightly different, it might have become one of the great comets of the early 21st century. Millions of people might have stood in their yards and parks, looking up at a brilliant celestial visitor, creating memories that would last lifetimes. Instead, Atlas became a cautionary tale about the unpredictability of comets and the fragility of these ancient objects. But perhaps there's a different kind of beauty in what actually happened. Instead of a single spectacular event, we got to witness something rarer and in some ways more profound. the slow dissolution of an ancient object, the gentle coming apart of something that had existed since before the Earth was formed. He watched as Atlas transformed from a single comet into multiple fragments, each going its own way, each carrying its piece of the story forward. It was death and birth simultaneously, an ending that was also a beginning, a single chapter closing while multiple new chapters opened. The promise unfulfilled by Atlas might yet be fulfilled by other members of its proposed family. If there are indeed other fragments of the parent comet out there, still approaching on their long orbits from the outer darkness, one of them might become the spectacular comet that Atlas failed to be. Perhaps in 50 years, or 100, or 500, another fragment will arrive, structurally sound enough to survive solar approach, large enough to become brilliant, positioned perfectly for observation from Earth. When that happens, if it happens, observers might look back at Atlas and the Great Comet of 1844 and recognize the family resemblance, adding another piece to this multi-century puzzle. The story of Atlas also highlights the importance of continuous observation and record-keeping in astronomy. The connection to the Great Comet of 1844 would never have been recognized without the careful observations made by 19th century astronomers, preserved in journals and logbooks, digitized and made available to modern researchers. Every observation, even of a comet that disappoints, becomes part of the permanent record, potentially useful to future astronomers in ways we can't anticipate. The sketches and measurements made by amateur astronomers observing Atlas might prove crucial to someone studying cometary fragmentation decades from now. As we reflect on the promise and disappointment of Atlas, we're reminded that the universe doesn't owe us spectacles. It operates according to its own rules, its own timescales, its own logic. Comets come and go, they brighten and fade. They survive or fragment according to forces and factors we're still trying to fully understand. Our role is to observe, to record, to learn, and to appreciate whatever the cosmos chooses to show us, whether it's a brilliant comet that lights up the night or a fragmenting nucleus that teaches us about the fragility of these ancient messengers. The fragments of Atlas are still out there, continuing their orbit, carrying their cargo of ancient ice and dust around the sun. They're fainter now, harder to see, but they're still part of the story. In a few thousand years, when they return to the inner solar system, humanity might have spread throughout the solar system, might have technologies we can't imagine, might observe these fragments with instruments that can read their entire history and their composition and structure. Or perhaps humanity won't be here at all, and the fragments will pass by unseen, unrecorded, their ancient journey continuing without witnesses. But for now, in this moment, we can appreciate what Atlas taught us even in its failure to become spectacular. We learned about cometary fragmentation, about the structural weakness of these ancient objects, about the possible family connection to historical comets. We were reminded of the unpredictability of nature and the importance of managing our expectations. And we were given a front row seat to a cosmic transformation, watching as something billions of years old came apart before our eyes, not with violence, but with a kind of gentle resignation, as if the comet had simply decided it had travelled long enough as a single entity and was ready to continue its journey in multiple forms. The promise of Atlas was ultimately not the promise of spectacle, but the promise of knowledge, of connection, of continuity with the past and future. In that sense, the promise was fulfilled, just not in the way we expected. Atlas connected us to the Great Comet of 1844, to the ancient parent comet, to the Oort cloud, to the formation of the solar system. It reminded us that we're part of a story that began long before us and will continue long after us, a story written in ice and orbit, in light and darkness, in the patient dance of celestial objects following their ancient paths through space. As we move forward in our exploration of this cosmic mystery, let's carry with us the lesson of Atlas, that the universe's gifts don't always come in the packages we expect. That disappointment can lead to discovery, that even in dissolution there is beauty and meaning. the fragments of Atlas, spreading out through space, are like seeds scattered on the cosmic wind, each one carrying the potential for future wonder, future discovery, future moments when humanity looks up and recognizes something familiar in a new, celestial visitor. Another piece of the puzzle, another chapter in the never-ending story of our solar system's icy wanderers. If Atlas and the Great Comet of 1844 are indeed siblings, fragments of the same parent comet, then logic suggests there should be other family members, other pieces of that ancient ice mountain that broke apart millennia ago. The search for these additional fragments takes us into the realm of celestial detective work, where astronomers combine historical records, orbital calculations, and modern observations to piece together family relationships separated by centuries or millennia. It's like trying to reconstruct a family tree where the family members only appear once every 1,000 years, and some of them might have changed their names or appearances in the interim. The process of identifying comet families begins with orbital analysis. When a comet is observed, astronomers calculate its orbital elements, those 6 numbers that completely describe its path through space. For members of the same family, 5 of these 6 elements should be very similar. The 6th element, the time of perihelion passage, will be different for each fragment, as they've spread out along the orbit over time, but even this spreading follows predictable patterns. If we know when the fragmentation occurred and the initial separation velocities, we can calculate when different fragments should arrive. The challenge is that cometary orbits aren't static. Every time a comet passes through the inner solar system, gravitational perturbations from the planets alter its orbit slightly. Jupiter, with its massive gravity, is particularly influential. A comet that passes within a few astronomical units of Jupiter can have its orbit significantly changed. Over multiple orbits, these perturbations accumulate, potentially obscuring family relationships. A comet that was clearly a family member 1,000 years ago might have an orbit today that looks quite different from its siblings. This is where historical observations become crucial. Chinese astronomers have been recording comets for over 2,000 years, providing the longest continuous record of cometary observations. Islamic astronomers during the medieval period made precise observations that help us track comets through the centuries. European observations become increasingly detailed from the Renaissance onward. By combining these historical records with modern computational techniques, astronomers can work backward, unwinding the gravitational perturbations to see what orbits looked like in the past. For the proposed Atlas 1844 family, several historical comets emerge as possible members. The comet of 1500 observed across Europe and Asia is one candidate. Described as a bright comet with a long tail, visible for several weeks, it appeared in a part of the sky consistent with the Atlas 1844 orbit. The observations aren't precise enough to calculate a definitive orbit, but what we can reconstruct is suggestive. If this was indeed a family member, it would have been one of the larger fragments, comparable in size to the Great Comet of 1844. Going further back, the comet of 539 AD, recorded in Chinese texts as a guest star with a tail, might be another family member. The Chinese astronomers noted that it appeared in the constellation we call Andromeda and moved through Perseus, a path consistent with the Atlas 1844 orbit. They described it as visible for more than a month, suggesting a substantial nucleus, but again, the observations aren't precise enough for certainty. We're dealing with descriptions like 3 hand widths from the bright star rather than exact coordinates. Even more tantalizing are references to comets in ancient texts that might be family members, but are described in mythological rather than astronomical terms. The Babylonians, keen observers of the sky, recorded many celestial events on cuneiform tablets. Some of these might describe comets from our family, but translating astronomical meaning from mythological language is challenging. When a Babylonian text describes the weapon of Marduk appearing in the house of Enlil, are we reading about a comet, a meteor, or something else entirely? The search for family members isn't limited to historical records. Modern sky surveys are constantly discovering new comets. and each one is checked against known families. The Catalina Sky Survey, Atlas, the survey that discovered Comet Atlas, Pan-STARRS, and other programs scan the sky every clear night, using sophisticated software to identify moving objects against the background stars. When a new comet is discovered, its orbit is immediately calculated and compared to existing databases. Several faint comets discovered in recent decades have orbits that might be consistent with the Atlas 1844 family, though none as closely matched as these two. Comet C1988A1, Lilla, for example, has orbital elements that are suggestively similar, though not identical. It might be a family member whose orbit has been significantly perturbed, or it might be unrelated. Without physical samples to compare composition, we can't be certain. The idea of a stream of fragments also raises the possibility of meteor showers associated with this comet family. As comets orbit the Sun, they leave trails of dust and small particles along their path. When Earth crosses one of these trails, we see a meteor shower. The Perseids, Leonids, and other annual showers are all associated with specific comets. If the Atlas 1844 family has been depositing debris along its orbit for thousands of years, there should be a meteor stream associated with it. The challenge is identifying this stream among the many meteor showers, both major and minor, that Earth encounters each year. The orbit of the Atlas 1844 family doesn't obviously match any of the well-known showers, but there are numerous minor showers, some producing only a few meteors per hour, that haven't been definitively linked to parent comets. One of these might be our family's meteor stream, unrecognized because it's too weak or too spread out to be obvious. There's also the possibility that Earth doesn't currently intersect the meteor stream but might in the future. Orbital evolution due to planetary perturbations and radiation pressure can cause meteor streams to drift over time. A stream that misses Earth today might intersect our orbit in a few centuries. Conversely, a meteor shower that our ancestors observed might no longer be visible because the stream has drifted away. The Chinese recorded several meteor showers in ancient times that don't correspond to any modern shower, possibly because the streams have evolved away from Earth's orbit. The distribution of fragments from a cometary breakup follows interesting patterns. When a comet nucleus fragments, the pieces don't separate randomly. The fragmentation often occurs along pre-existing planes of weakness, boundaries between different components that were assembled when the comet first formed. The separation velocities are typically very small, just a few meters per second, but over time, these small differences lead to significant spreading along the orbit. The smallest fragments, dust and tiny ice grains, are most affected by non-gravitational forces like radiation pressure and solar wind. These particles can be blown out of their original orbits entirely, dispersing into interplanetary space or being pushed into orbits that no longer resemble the parents. Medium-sized fragments, from pebbles to boulders, are less affected by these forces but still experience some orbital evolution. The largest fragments, the ones that become comets in their own right, maintain orbits closest to the original, though even they experience gradual changes. This size-dependent spreading means that a comet family isn't a discrete group, but rather a continuum of objects ranging from large cometary nuclei down to microscopic dust grains, all related but following increasingly divergent paths. It's like a family reunion, where some members have stayed close to home while others have scattered across the globe, maintaining a connection but living very different lives. The search for family members is complicated by the fact that comets can be difficult to detect when they're far from the Sun. A comet nucleus, without its coma and tail, is just a dark chunk of ice and dust, reflecting very little sunlight. Even a large comet can be invisible beyond Jupiter's orbit with current technology. This means there might be family members already on their way in from the outer solar system, destined to become visible in the coming decades but currently undetectable. Future telescopes might change this. The Vera Rubin Observatory, with its large synoptic survey telescope, will survey the entire visible sky every few nights, detecting objects far fainter than current surveys can see. The Nancy Grace Roman Space Telescope will conduct infrared surveys that might detect the heat signature of approaching comets while they're still in the outer solar system. These instruments might reveal family members we don't yet know exist, filling in gaps in our understanding of the Atlas 1844 family tree. The concept of comet families also connects to broader questions about the solar system's evolution. If comets fragment regularly, producing families of objects, then the population of comets should be increasing over time. But we also know that comets have finite lifetimes, eventually sublimating away entirely or becoming inactive. The balance between creation through fragmentation and destruction through sublimation determines the steady-state population of active comets. Studies suggest that the current population of active short-period comets can't be maintained by captures from the Oort cloud alone. There must be additional sources, and fragmentation is one possibility. Each fragmentation event multiplies the number of active comets, at least temporarily. This multiplication might be crucial for maintaining the population we observe. In this view, comet families aren't just interesting genealogical puzzles, but essential components of the solar system's cometary ecosystem. The Atlas 1844 family, if confirmed, would be particularly interesting because of its long period. Most well-studied comet families consist of short-period comets that return every few years to decades. These families can be observed multiple times within human lifetimes, allowing astronomers to track their evolution. Long-period families are much harder to study because we might see each member only once in recorded history. The Atlas 1844 family gives us a rare opportunity to study a long-period family, albeit one where we're piecing together observations separated by centuries. The chemical composition of family members provides another way to test relationships. Each comet has a unique chemical fingerprint determined by the ratios of different ices, the isotopic composition of various elements, and the types of dust grains present. Family members should have very similar compositions, having originated from the same parent body. For Atlas, we have modern spectroscopic observations that reveal its chemical makeup. We can detect water, of course, but also carbon monoxide, carbon dioxide, ammonia, methane, and various organic molecules. For historical comets like the Great Comet of 1844, we don't have such detailed compositional data. However, some historical observations provide clues. Observers often noted the color of comets, which can indicate composition. A yellowish comet typically has a high dust content, while a greenish tinge comes from diatomic carbon. The Great Comet of 1844 was described as having both colors at different times, suggesting a complex composition with both dust and gas components. Future technology might allow us to study the composition of historical comets in unexpected ways. When a comet passes through the inner solar system, it deposits material along its path. Some of this material eventually falls to Earth as micrometeorites. These particles accumulate in places like Antarctic ice and deep sea sediments. By drilling ice cores or sediment cores and looking for layers corresponding to historical comet passages, we might recover actual material from comets observed centuries ago. Analyzing these particles could provide the compositional data we need to confirm family relationships. The study of comet families also has implications for planetary defense. If comets fragment regularly and create families of objects following similar orbits, then discovering one family member might alert us to others. If we know that a comet is part of a family, we can calculate when other fragments might arrive and whether any of them pose an impact risk to Earth. While the probability of a comet impact is extremely low, the consequences could be severe, making early detection crucial. The Atlas 1844 family, with its long period and relatively distant perihelion, poses no threat to Earth. The orbits don't come close enough to our planet for impact to be possible. But studying this family helps us understand the fragmentation process and family dynamics, knowledge that could be applied to other comet families that might include Earth crossers. Every family we identify and study adds to our understanding of these complex systems. The cultural impact of comet families is also worth considering. Throughout history, bright comets have been interpreted as omens, incorporated into religious and mythological narratives, and used to mark significant events. If some of these historical comets were actually members of the same family, returning fragments of an ancient parent, it adds a layer of continuity to these cultural interpretations. Different cultures at different times might have been responding to the same cosmic phenomenon, seeing different chapters of the same story. For example, if the comet of 1500 was indeed a member of the Atlas 1844 family, then Renaissance Europeans who saw it as a sign of impending change were looking at a sibling of the comet that 19th century observers would carefully measure and 20th century astronomers would photograph. The same cosmic object, or at least fragments of the same parent, have been weaving through human history, each appearance interpreted through the lens of its time but all connected by their common origin. The possibility of undiscovered family members still approaching adds an element of anticipation to this story. Somewhere in the outer solar system, perhaps beyond Neptune's orbit, there might be another fragment of the parent comet, slowly falling toward the Sun. It might arrive in 50 years, or 100, or 500. When it does, astronomers will calculate its orbit, compare it to historical comets, and perhaps recognize it as another member of the Atlas 1844 family. This future comet might be the spectacular one that Atlas failed to become. With a larger nucleus or more favorable geometry, it might become a great comet visible to the naked eye, inspiring wonder and making headlines. People might gather to observe it, not knowing they're looking at a sibling of Atlas, a cousin of the great comet of 1844, another fragment of that ancient parent that broke apart when human civilization was young, or perhaps before it began. The search for these family members continues with every new comet discovery, every refinement of orbital calculations, every improvement in our understanding of cometary dynamics. It's a puzzle that might never be completely solved, as some family members have probably already been destroyed, sublimated away entirely or fallen into the Sun. Others might be too faint ever to detect, but each piece we find adds to our understanding, helping us reconstruct the story of this ancient comet and its slow transformation from a single object into a family spread across space and time. The family of fragments that might include Atlas and the Great Comet of 1844 represents more than just an interesting astronomical puzzle. It's a window into the processes that shape our solar system, a demonstration of the complex dynamics that govern celestial objects, and a reminder of the deep connections that link observations separated by centuries. When we recognize these family relationships, we're reading the autobiography of the solar system, written in ice and orbit, fragmentation and reformation, ancient history and future possibility. As we contemplate this family of fragments, we're drawn to think about the ultimate source of all comets, the vast and mysterious region from which they originate. To truly understand Atlas, the Great Comet of 1844, and their hypothetical siblings, we need to journey to the edge of our solar system and beyond, to a realm so distant and dark that the Sun itself appears as merely the brightest star among many. We need to explore the Oort cloud, that spherical shell of icy bodies that surrounds our solar system like a cosmic snow globe, holding trillions of potential comets in a state of perpetual frozen suspension, waiting for the gentle gravitational nudge that will send them falling toward the inner solar system and their eventual destiny as the spectacular visitors we observe from Earth. The Oort cloud exists in a realm of darkness so profound that human imagination struggles to comprehend it. Picture yourself drifting outward from the Sun, past the familiar planets, past Neptune's deep blue atmosphere, past the Kuiper belt where Pluto resides with its companions, continuing outward until the Sun has shrunk to just another point of light, bright perhaps, but not dramatically different from other stars. Keep going, and going, and going, until you've travelled 1,000 times farther from the Sun than Earth, then 2,000 times, then 10,000 times. Here, in this ultimate darkness, in this coldest of cosmic freezers, lies the Oort cloud, a spherical shell of icy bodies that has remained essentially unchanged since the birth of our solar system 4.6 billion years ago. This is the quiet nursery of comets, the repository of ancient ice that holds within it the story of our solar system's formation. The Oort cloud is thought to extend from about 2,000 astronomical units from the Sun to perhaps 100,000 astronomical units or more, nearly halfway to the nearest star. To put this in perspective, if the distance from Earth to the Sun were shrunk to 1 inch, Neptune would be about 30 inches away, but the inner edge of the Oort cloud would be more than 150 feet distant, and its outer edge would be nearly 1.5 miles away. It's a scale that defeats ordinary comprehension, a vastness that makes even our solar system's planets seem huddled close to the Sun's warmth. In this immense volume of space, drifting in eternal darkness, are perhaps trillions of cometary nuclei. These aren't active comets with bright tails. Those only develop when a comet approaches the Sun. Out here, they're just chunks of ice and dust, frozen solid at temperatures only a few degrees above absolute zero. They move slowly, incredibly slowly, taking millions of years to complete a single orbit around the distant Sun. They've been out here since the beginning, exiled from the inner solar system during the chaotic early days when the planets were forming and migrating to their current positions. The story of how the Oort cloud formed is the story of the solar system itself. When our Sun was born from a collapsing cloud of gas and dust, it was surrounded by a disk of material from which the planets would eventually form. In the inner parts of this disk, where temperatures were high, only rocky materials could condense, forming the terrestrial planets Mercury, Venus, Earth, and Mars. Farther out, beyond what astronomers call the frost line, temperatures were cold enough for water ice to form, and the giant planets, Jupiter, Saturn, Uranus, and Neptune, began to grow, their massive gravity allowing them to capture hydrogen and helium from the surrounding nebula. But not all the material in the disk ended up in planets. Countless smaller bodies, called planetesimals, formed throughout the disk. In the outer regions, these planetesimals were rich in ice, water ice certainly, but also frozen methane, ammonia, carbon dioxide, and other volatile compounds. As the giant planets grew and began to migrate through the disk, their gravity scattered these icy planetesimals in all directions. Some were thrown out of the solar system entirely, becoming interstellar wanderers. Others were thrown into the distant spherical cloud that we now call the Oort cloud. This process of scattering wasn't gentle. The planetesimals that ended up in the Oort cloud experienced violent gravitational encounters with the giant planets, particularly Jupiter and Neptune. They were flung outward at tremendous speeds. Their orbits changed from relatively circular paths in the plane of the planets to highly elongated orbits oriented in all directions. This is why the Oort cloud is spherical rather than disc-shaped like the Kuiper belt. The scattered planetesimals came from all parts of the original disk and were thrown out in all directions. Once in the Oort cloud, these icy bodies found a kind of peace. Far from the Sun's heat and the gravitational perturbations of the planets, they could orbit quietly for billions of years. The environment out there is extraordinarily stable. The temperature hovers just a few degrees above absolute zero, cold enough that even molecules that would be gases anywhere in the inner solar system are frozen solid. There's no weather, no seasons, no day or night in any meaningful sense. Just darkness, cold, and the slow, patient circling of the distant Sun. But the Oort cloud isn't completely isolated from outside influences. Other stars pass by our solar system, usually at distances measured in light years but occasionally closer. When a star passes within a few light years, its gravity can perturb the orbits of Oort cloud objects, nudging some of them into new paths. The galaxy itself exerts tidal forces on the Oort cloud, the collective gravity of billions of stars creating subtle influences that accumulate over millions of years. And occasionally, though rarely, our solar system passes through regions of slightly higher density in the galaxy, molecular clouds or spiral arms, which can also disturb the Oort cloud. These perturbations are usually tiny, barely noticeable on short timescales, but given enough time, and the Oort cloud has had billions of years, they can change an object's orbit enough to send it falling toward the inner solar system. The journey from the Oort cloud to the Sun is a long one, taking millions of years. The comet starts its fall from essentially zero velocity relative to the Sun, slowly accelerating under the Sun's weak but persistent gravitational pull. As it falls inward, it gains speed, its orbit bending into an increasingly elongated ellipse. The comet that would eventually fragment to create Atlas and the Great Comet of 1844 must have begun its journey this way, nudged from its stable Oort cloud orbit by some random gravitational perturbation millions of years ago. Perhaps it was a passing star, or the accumulated effect of galactic tides, or a combination of influences. Whatever the cause, this ancient chunk of ice began its long fall toward the Sun, carrying with it materials that had been frozen since the solar system's birth. As our proto-comet fell inward, it passed through regions of space that no human eyes have ever seen directly. The outer Oort cloud is so distant and dark that even our most powerful telescopes can't detect individual objects there. We infer its existence from the orbits of long-period comets, which seem to come from all directions, and have orbital periods ranging from hundreds to millions of years. The randomness of their orbital orientations tells us the cloud must be spherical, and the distribution of their orbital periods tells us about the cloud's extent. The inner Oort cloud, sometimes called the Hills cloud, is thought to be somewhat denser and more disc-shaped, a transition zone between the spherical outer cloud and the Kuiper belt. Our comet would have passed through this region, perhaps experiencing additional gravitational perturbations that further modified its orbit. It's possible that interactions in the inner Oort cloud are what set the comet on its final trajectory toward the Sun, determining the specific orbital parameters that we would later observe in Atlas and the Great Comet of 1844. The Oort cloud is thought to contain an enormous amount of material, perhaps several Earth masses in total, but spread over such a vast volume that the average distance between objects is enormous. If you were floating next to an Oort cloud comet, you probably wouldn't be able to see another one with the naked eye. They'd be too far away and too dark. It's a lonely place, a vast emptiness punctuated by occasional chunks of ancient ice, each one isolated in its own orbit, unaware of its neighbours. Yet despite this isolation, the objects in the Oort cloud are all related, all formed from the same protoplanetary disk, all composed of similar materials. They're like a vast extended family, scattered across an enormous volume but sharing a common origin. When we see a long-period comet like Atlas, we're seeing a representative of this family, an ambassador from the edge of the solar system, bringing us information about conditions during the solar system's formation. The composition of Oort cloud comets tells us about the environment in which they formed, the presence of certain molecules, the ratios of different isotopes, the types of dust grains embedded in the ice. All these provide clues about temperature, pressure, and chemical conditions in the early solar system. For instance, the ratio of deuterium to hydrogen in cometary water tells us about the temperature at which the water formed. The presence of complex organic molecules tells us about the chemistry that was possible in the cold outer regions of the protoplanetary disk. Atlas, during its brief appearance in 2020, was studied spectroscopically, revealing its composition. Astronomers detected water vapor as expected, but also carbon monoxide, carbon dioxide, and various organic molecules including methanol and formaldehyde. These are the building blocks of more complex organic chemistry, the kinds of molecules that, given the right conditions, could lead to the formation of amino acids and other prebiotic compounds. Every comet from the Oort cloud carries this chemical heritage, these frozen samples of the early solar system's organic inventory. The idea that comets might have delivered water and organic molecules to the early Earth is one of the most intriguing aspects of cometary science. During the period called the Late Heavy Bombardment, roughly 4 billion years ago, the inner solar system was pelted with comets and asteroids. This bombardment might have delivered much of Earth's water and the organic molecules that would eventually lead to life. If this is true, then we owe our existence in part to comets from the Oort cloud, ancient messengers that brought the ingredients for life from the cold, outer reaches of the solar system. But the Oort cloud isn't just a source of comets, it's also a record of the solar system's history and its interactions with the galaxy. The structure of the Oort cloud, its inner and outer components, the distribution of orbits within it, all tell us about the environment in which the solar system formed and evolved. For instance, the outer edge of the Oort cloud is determined by the point at which the sun's gravity becomes weaker than the tidal forces of the galaxy. Objects beyond this point would be stripped away, becoming interstellar wanderers. The sun probably formed in a stellar nursery, a region where many stars were born from the same molecular cloud. These sibling stars would have been much closer together than stars typically are today, perhaps close enough to exchange Oort cloud objects. Some of the comets in our Oort cloud might actually have formed around other stars, captured by the sun during the early chaotic period when the stellar nursery was dispersing. Conversely, some objects that formed in our solar system might now be orbiting other stars or wandering in interstellar space. This exchange of material between stellar systems adds another layer of complexity to the story of comets. When we observe a comet from the Oort cloud, we might be looking at something that formed around another star entirely, a true interstellar visitor that's been part of our solar system for billions of years. The discovery of Oumuamua and Borisov, the first confirmed interstellar objects to pass through our solar system, has shown us that such exchanges are possible, even today, when stars are much farther apart. The Oort cloud also serves as a buffer zone between our solar system and interstellar space. It's the first thing that interstellar objects encounter when approaching our sun, and the last thing that escaping objects pass through. This boundary region is constantly evolving, losing objects that are perturbed into interstellar space, and possibly capturing objects that happen to pass by with the right trajectory and velocity. It's a dynamic equilibrium maintained over billions of years. The quiet nursery of the Oort cloud has profound implications for our understanding of planetary systems in general. Other stars probably have their own Oort clouds, their own reservoirs of comets waiting in the darkness. When we observe exoplanets, we're seeing only the inner parts of those systems. The Oort clouds around other stars are far too distant and dark to detect with current technology, but they're probably there, and they probably play similar roles in those systems as our Oort cloud does in ours. The stability of the Oort cloud over billions of years is remarkable when you consider all the forces acting on it. Passing stars, galactic tides, molecular clouds, the gradual evolution of the sun itself. All these influences could potentially disrupt the cloud, yet it persists, continuously sending comets toward the inner solar system, maintaining a steady supply of these ancient messengers. This stability suggests that the Oort cloud is robust, able to withstand perturbations that might seem significant on short timescales, but average out over cosmic time. The future of the Oort cloud is tied to the future of the solar system and the sun itself. As the sun ages and eventually becomes a red giant billions of years from now, its increased luminosity will affect the inner parts of the Oort cloud. Objects that have been frozen for billions of years might begin to sublimate even at those enormous distances. Later, when the sun sheds its outer layers and becomes a white dwarf, the reduced gravity will allow some Oort cloud objects to escape into interstellar space. The cloud that has been a feature of our solar system since its birth will slowly disperse, its components becoming interstellar wanderers. But that's billions of years in the future. For now, the Oort cloud continues its quiet existence, a vast repository of ancient ice waiting in the darkness. Every few years, one of its members begins the long fall toward the sun, eventually becoming a comet that might grace our skies. Atlas was one of these, as was the Great Comet of 1844 and their hypothetical parent before them. Each one is a messenger from this distant realm, a sample of material that's been preserved since the beginning, a frozen time capsule waiting to be opened. The connection between the Oort cloud and the comets we observe is direct and profound. Every long-period comet is a piece of the Oort cloud made visible, a chunk of that distant dark realm brought into the light. When we study these comets, we're studying the Oort cloud itself, learning about its composition, structure, and history. Each comet is a scientific probe launched millions of years ago, finally reporting back with data about the edge of our solar system. The Oort cloud also represents the ultimate recycling system. Material that was processed in the early solar system, perhaps even cycled through the first generation of planetesimals that were destroyed in collisions, was eventually scattered to the Oort cloud where it's been stored for billions of years. Now, piece by piece, comet by comet, this material is returning to the inner solar system. Some of it falls into the sun, some impacts planets, some gets ejected from the solar system entirely. It's a slow process of redistribution that's been going on since the beginning, and will continue until the sun dies. As we think about Atlas and its journey from the Oort cloud, we can imagine the countless other comets still out there, each on its own orbit, each with its own eventual destiny. Some are already falling toward the sun, though they won't arrive for millions of years. Others are perfectly stable, destined to orbit in the darkness forever unless perturbed by some future stellar encounter. Still others are on the verge of escape, one small perturbation away from becoming interstellar wanderers. The Oort cloud is often described as a reservoir, but it's really more like a library, a vast collection of books written in ice and dust, each one containing information about the early solar system. We can only read the books that happen to fall toward the sun and become comets, and we can only read them during their brief period of activity before they fade away. But each one we do read adds to our knowledge, helps us understand the story of our origins, connects us to the deep history of our cosmic neighborhood. The parent comet of Atlas and the great comet of 1844 spent most of its existence in this quiet nursery, orbiting slowly in the darkness, unchanged for billions of years. When it finally began its journey toward the sun, it was carrying information about the Oort cloud, about the early solar system, about the conditions that existed when the planets were forming. Its fragmentation and the subsequent evolution of its pieces is just the latest chapter in a story that began with the birth of the sun and will continue long after human civilization has ended. The Oort cloud reminds us of the vast scales of space and time that govern the cosmos. It exists in a realm so distant that light from the sun takes months or years to reach it. Objects there orbit so slowly that a single circuit around the sun takes longer than the entire history of human civilization. Yet this distant, dark, quiet place is intimately connected to us. The water in our oceans might have come from there. The organic molecules that led to life might have been delivered by comets from the Oort cloud. We are, in a very real sense, children of the Oort cloud, assembled from materials that once drifted in that ultimate darkness. As we prepare to explore what messages these ancient travellers might carry, what stories are locked in their ice, we carry with us this image of the Oort cloud, a vast spherical shell of possibilities, each frozen chunk a potential comet, a potential messenger, a potential key to understanding our origins. It's a place we've never seen directly and probably never will, but its influence reaches across the solar system and across time, connecting the distant past to the present and future, the edge of the solar system to Earth, the darkness to the light. Within every comet that visits our inner solar system lies a message written in molecules and isotopes, a chemical manuscript that's been preserved in the deep freeze of space for billions of years. Atlas, during its brief journey through our skies in 2020, was carrying such a message, one that modern instruments could partially decode before the comet fragmented and faded away. This ancient ice, older than Earth itself, older than life, nearly as old as the sun, contained within it clues about the conditions that existed when our solar system was just beginning to form from a collapsing cloud of gas and dust. The composition of a comet tells us first about the temperature at which it formed. Water ice, the primary component of most comets, can exist in different crystalline structures depending on the temperature at which it freezes. At the extremely low temperatures of the outer solar system, water ice can trap other molecules within its crystal structure, creating what scientists call clathrate hydrates. These are like molecular cages, with water molecules forming the bars and other molecules imprisoned inside. The types of molecules that can be trapped and the efficiency of trapping depend on temperature. So by studying what's released when a comet warms up, we can determine the temperature at which it originally formed. Atlas showed us a complex mixture of volatile compounds. Besides water, astronomers detected carbon monoxide and carbon dioxide, both common in comets but present in varying ratios that tell us about formation conditions. Carbon monoxide is extremely volatile, sublimating at temperatures far below those at which water ice becomes active. Its presence in Atlas suggested that the comet formed in an extremely cold environment, probably beyond 30 astronomical units from the Sun, consistent with an origin in the Kuiper belt or Oort cloud. The ratio of carbon monoxide to carbon dioxide provided additional constraints, suggesting formation temperatures below 50 Kelvin, colder than the coldest places in the current inner solar system. But the message in the ice goes beyond simple temperature indicators. The isotopic ratios in cometary molecules are like fingerprints of the environments in which they formed. Isotopes are versions of elements with different numbers of neutrons, and their ratios can tell us about the physical and chemical processes that were occurring when the molecules formed. The ratio of deuterium to hydrogen in cometary water, for instance, tells us about the temperature and location of water formation. Most comets have deuterium to hydrogen ratios about twice that of Earth's oceans, suggesting that comets weren't the only source of Earth's water, though they probably contributed significantly. The organic molecules detected in Atlas were particularly intriguing. Methanol, formaldehyde, hydrogen cyanide, and other simple organic compounds were present, the basic building blocks from which more complex organic chemistry can develop. These molecules didn't form in the comet itself, but were likely created in the cold molecular cloud from which our solar system formed, or in the protoplanetary disk around the young Sun. They've been preserved unchanged in the comet's ice for billions of years, a sample of the organic inventory available when planets were forming. The presence of these organic molecules raises profound questions about the origins of life. Laboratory experiments have shown that when ice containing these simple organics is exposed to radiation, cosmic rays in space or ultraviolet light from stars, more complex molecules can form, including amino acids, the building blocks of proteins. Some meteorites, which may be fragments of asteroids or comets, contain dozens of different amino acids, far more than the 20 used by life on Earth. This suggests that the basic ingredients for life were available throughout the early solar system, delivered by comets and asteroids to any planet lucky enough to have the right conditions for life to develop. The dust component of comets carries its own set of messages. Mixed in with the ice are tiny grains of material that predate the solar system itself. These pre-solar grains, formed around other stars, were ejected into interstellar space when those stars died, and were incorporated into the molecular cloud from which our solar system formed. They survived the formation of the Sun and planets, were incorporated into comets, and have been preserved there ever since. When we analyze cometary dust, either from spacecraft missions or from particles that reach Earth, we're literally holding stardust, material from stars that died before our Sun was born. The Stardust mission, which returned samples from Comet Wild 2 in 2006, revealed the incredible diversity of materials in cometary dust. There were grains that formed at extremely high temperatures, probably close to the young Sun, mixed with grains that formed in the cold outer regions of the solar system. This mixing suggests that material was transported across the entire protoplanetary disk, from the hot inner regions to the cold outer regions where comets formed. It's evidence of a dynamic, turbulent early solar system where materials were thoroughly mixed before being frozen into the comets we see today. Atlas, being observed only telescopically, couldn't provide us with physical dust samples, but spectroscopic observations revealed the presence of silicate grains, indicated by their characteristic infrared emission. The specific wavelength suggested a mixture of crystalline and amorphous silicates, again pointing to a combination of materials processed at different temperatures. This heterogeneity is a common feature of comets, and tells us that these objects are not simple, uniform snowballs but complex aggregates of materials with diverse histories. The fragmentation of Atlas provided an unexpected opportunity to see deeper into the comet's interior. As the nucleus broke apart, fresh surfaces were exposed, surfaces that hadn't seen sunlight for billions of years. The composition of these newly exposed areas was subtly different from the original surface, showing variations in the ratio of different ices and the size distribution of dust grains. This heterogeneity suggests that the comet formed from multiple smaller bodies that came together in the early solar system, each with slightly different compositions, creating a composite object with a complex internal structure. The organic molecules in comets aren't just simple compounds, but include complex carbon chains and ring structures. Some comets have been found to contain glycine, the simplest amino acid, detected both in samples returned from Comet Wild 2 and in the coma of several other comets through spectroscopy. The presence of amino acids in comets supports the idea that these objects could have seeded early Earth with the building blocks of life. Every comet impact on the early Earth would have delivered a package of organic molecules, water, and energy, potentially creating local environments where more complex chemistry could occur. The message in ancient ice extends beyond chemistry to physics. The structure of cometary nuclei tells us about the processes by which planetesimals formed in the early solar system. The low density of cometary nuclei, typically less than that of water ice, indicates that they're highly porous, more like loosely packed snowballs than solid chunks of ice. This structure is consistent with formation through gentle accretion of smaller particles in the low-gravity environment of the outer solar system. The particles came together slowly, sticking through weak forces, creating the fragile structures we observe today. The spin rates of cometary nuclei provide another piece of information. Most comets rotate slowly with periods of hours to days. This slow rotation suggests that they haven't experienced significant collision since their formation. A major impact would likely have spun them up or broken them apart. The fact that comets like Atlas can survive for billions of years with such fragile structures tells us that the Oort cloud and Kuiper belt are remarkably peaceful places, with objects orbiting in isolation, rarely interacting with one another. The gases released by comets as they approach the Sun create spectacular comae and tails, but they also provide real-time information about the comet's composition and the processes occurring on its surface. Different molecules sublimate at different temperatures, so as a comet approaches the Sun, we see a sequence of activations. First, the most volatile compounds like carbon monoxide become active far from the Sun. Then carbon dioxide joins in. Finally, as the comet gets closer, water ice begins to sublimate in earnest, often becoming the dominant component of the coma. This sequential activation creates a kind of chemical stratigraphy that we can observe remotely. By monitoring which molecules are being released at different distances from the Sun, we can infer the structure of the nucleus, with more volatile compounds potentially concentrated in certain regions or layers. Atlas showed this sequential activation clearly, with carbon monoxide emissions detected when the comet was still beyond Jupiter's orbit, while water didn't become dominant until the comet was much closer to the Sun. The isotopic ratios in cometary molecules provide connections to other objects in the solar system and beyond. The nitrogen isotope ratios in cometary ammonia and hydrogen cyanide are similar to those seen in the atmospheres of the giant planets and in some primitive meteorites, suggesting a common source or formation process. But they're different from the nitrogen isotope ratio in Earth's atmosphere, indicating that comets weren't the primary source of Earth's nitrogen. These isotopic fingerprints help us piece together the complex story of how different elements and compounds were distributed throughout the early solar system. One of the most intriguing aspects of the message in ancient ice is what it tells us about water in the solar system. Water is everywhere, in comets, in asteroids, on moons, in planetary atmospheres. But it's not all the same. The deuterium to hydrogen ratio varies significantly between different bodies, creating a kind of isotopic map of the solar system. Comets from the Oort cloud typically have high DH ratios, about twice that of Earth's oceans. Jupiter family comets, which come from the Kuiper belt, show more variation, with some matching Earth's ratio quite closely. This suggests that Earth's water came from multiple sources, possibly including both comets and asteroids, mixed in proportions we're still trying to determine. The noble gases trapped in cometary ice provide another set of clues. These chemically inert gases, helium, neon, argon, krypton, xenon, can be trapped in ice at very low temperatures, and their abundances and isotopic ratios tell us about the conditions in the early solar system. The argon to krypton ratio in comets, for instance, is different from that in the Sun, suggesting that some process in the early solar system fractionated these gases. Understanding this fractionation helps us understand the physical and chemical processes that were operating when the planets were forming. The discovery of phosphorus and sulfur compounds in comets adds another dimension to their potential role in the origins of life. Phosphorus is essential for life as we know it, being a key component of DNA, RNA, and ATP, the energy currency of cells. But phosphorus is relatively rare in the universe, and often locked up in minerals that aren't readily available for biology. Comets contain phosphorus in more accessible forms, potentially providing a source of this crucial element for early life. Similarly, sulfur compounds in comets could have contributed to the sulfur cycle that's important for many biological processes. The temporal aspect of the message in ancient ice is particularly fascinating. When we observe a comet, we're not just seeing the composition of the early solar system, we're seeing it preserved with minimal alteration for billions of years. It's like having a sample that was frozen at the moment of the solar system's birth and kept in perfect storage ever since. This preservation is never perfect. Cosmic rays can cause some chemical changes, and the very process of approaching the sun and becoming active alters the surface layers. But the bulk of the nucleus remains remarkably pristine. The comparison between different comets allows us to map variations in the early solar system. Comets that formed at different distances from the Sun, or at different times during the solar system's formation, should have slightly different compositions. By studying many comets, we can begin to reconstruct the chemical and physical gradients that existed in the protoplanetary disk. Atlas and the Great Comet of 1844, if they're truly siblings from the same parent, provide a particularly valuable data point because they give us multiple samples from the same original object, allowing us to study both the composition and the heterogeneity of a single primordial comet. The message in ancient ice also includes information about the broader universe beyond our solar system. The pre-solar grains in cometary dust carry isotopic signatures of nuclear processes in other stars. Some grains show evidence of formation in the atmospheres of red giant stars, others in the explosive environments of supernovae. By studying these grains, we learn not just about our own solar system, but about the stellar processes that created the elements from which our solar system formed. Every comet is thus a messenger not just from the early solar system, but from the stars that came before. The organic molecules in comets connect us to the broader question of whether the building blocks of life are common throughout the universe. The same simple organic molecules found in comets, methanol, formaldehyde, hydrogen cyanide, are also detected in interstellar molecular clouds, in the atmospheres of other planets, and in protoplanetary disks around young stars. This ubiquity suggests that organic chemistry is a natural consequence of the conditions in space, that the universe naturally produces the building blocks of life. Comets are local delivery vehicles for this cosmic organic inventory. As we delve deeper into the message carried by Atlas and other comets, we're struck by the interconnectedness of everything in the solar system. The water in Earth's oceans, the organic molecules that became life, the noble gases in our atmosphere, even some of the dust in our homes, all of these have connections to comets, to the ancient ice that's been orbiting in the darkness for billions of years. When we study comets, we're not studying alien objects, but distant relatives, family members that share our origins but have lived very different lives, preserved in the cold while Earth became warm and alive. The fragmentation of Atlas, disappointing as it was for those hoping for a spectacular show, provided its own valuable message. The way the comet came apart, the rate at which the fragments separated, the continued activity of the individual pieces, all of these observations tell us about the internal structure of the nucleus, about how these ancient objects are put together. The fragmentation was like a cosmic dissection, revealing the comet's internal anatomy in a way that no spacecraft mission could have achieved. Each fragment continued to sublimate, continued to release its ancient gases, continued to deliver its message even as the comet as a whole ceased to exist. The story written in ancient ice is far from complete. Each new comet we observe adds another page, another perspective, another piece of the puzzle. Future missions to comets, advanced spectroscopic techniques, and perhaps even sample return missions to multiple comets will help us read this message more clearly. The European Space Agency's Comet Interceptor mission, planned for launch in the late 2020s, will wait in space for a pristine comet from the Oort cloud to approach, then intercept it for close-up study. Such missions will provide unprecedented detail about the messages these ancient travelers carry. But even with our current understanding, the message is profound. Comets tell us that we're made of recycled stardust, that water and organic molecules were abundant in the early solar system, that the ingredients for life were delivered to Earth by these icy messengers. They tell us about temperatures and pressures in the protoplanetary disk, about the mixing of materials from different regions, about the processes that built planets from dust and ice. They connect us to the stars that came before our sun, to the molecular clouds from which solar systems form, to the cosmic processes that create and distribute the elements. As we contemplate this message in ancient ice, we're really contemplating our own origins. Every molecule of water we drink, every carbon atom in our bodies, every breath we take contains atoms that have been on an incredible journey, formed in stars dispersed into space, incorporated into our solar system, possibly stored in comets for billions of years, delivered to Earth, cycled through geology and biology countless times, and finally assembled into us. Comets like Atlas are reminders of this journey, messengers from the deep past carrying news of our cosmic heritage. The message continues to arrive with each new comet, each fragment of ancient ice that falls from the Oort cloud toward the sun. Some messages are clear and dramatic, delivered by great comets that blaze across the sky. Others are subtle, visible only to sensitive instruments, decoded only through careful analysis. But each one adds to our understanding, helps us piece together the story of our origins, connects us to the vast scales of space and time that govern the universe. The ancient ice speaks, and we, products of the same cosmic processes that created the comets, have developed the ability to listen and understand. We come now to the end of our journey through this cosmic mystery, though in truth, the story has no real ending, only a continuous unfolding that stretches from the deep past into the indefinite future. The question we began with, was Comet Atlas known before it was found, has led us through centuries of human observation, billions of years of solar system history, and out to the very edge of our cosmic neighborhood. Along the way, we've discovered that this isn't just a story about two comets that might be related, but about the fundamental processes that shape our solar system, about the origins of water and organic molecules, about the deep connections between Earth and the cosmos. The possibility that Atlas and the Great Comet of 1844 are siblings, fragments of the same ancient parent, remains unproven but compelling. The evidence, their remarkably similar orbits, the fragmentation behavior of Atlas, the historical patterns of cometary families, all points toward a connection that spans centuries. If this connection is real, It transforms our understanding of these objects from isolated events to chapters in a much longer story, a multi-generational saga of cosmic ice slowly coming apart and returning to the inner solar system piece by piece. But even if future observations somehow disprove this connection, even if Atlas and the Great Comet of 1844 turn out to be unrelated after all, the journey of exploration has been worthwhile. We've learned about the processes that create and destroy comets, about the vast reservoir of ancient ice that surrounds our solar system, about the messages encoded in molecules and isotopes. We've connected human observations across centuries, linking the candle-lit observatories of 1844 to the space telescopes of 2020, showing how science builds on itself, each generation adding to the accumulated knowledge of humanity. The unfinished nature of this story is perhaps its most beautiful aspect. Somewhere out there, beyond the orbit of Neptune, beyond the Kuiper belt, other fragments of the hypothetical parent comet might be falling toward the Sun. They could arrive in decades, centuries, or millennia from now. When they do, future observers, perhaps still human, perhaps something else entirely, will have the opportunity to add new chapters to this story. They'll have tools we can't imagine, techniques we haven't dreamed of, understanding we haven't achieved. But they'll be building on the foundation we've laid, just as we've built on the observations of those who came before us. This continuity across time is one of the most profound aspects of astronomy. When we observe a comet, we're participating in a tradition that goes back to the dawn of human consciousness. Our ancestors looked up at comets with wonder and fear, weaving them into myths and legends, seeing them as omens and portents. Medieval astronomers tracked them across the sky, trying to understand their nature. Renaissance scientists began to calculate their orbits, realizing they were physical objects following mathematical laws. 19th century observers like those who witnessed the Great Comet of 1844 made careful measurements that we still use today. And now we observe with instruments that can detect individual molecules, that can see fragments the size of buildings from millions of miles away, that can reconstruct events that happened billions of years ago. Yet for all our technological advancement, the fundamental experience remains the same. We look up at a visitor from the depths of space and wonder about its origins, its meaning, its message. The wonder that Atlas inspired in 2020, even as it fragmented and faded, was the same wonder that the Great Comet of 1844 inspired in its observers. It's the same wonder that the parent comet, if it was ever visible from Earth, would have inspired in whoever was here to see it. This continuity of wonder connects us across centuries and millennia, a human constant in a universe of change. The scientific story we've traced, from the Oort cloud to the inner solar system, from ancient ice to modern spectroscopy, from a single parent comet to a family of fragments, is also a deeply human story. It's about our desire to understand our place in the universe, to find patterns and connections, to read meaning in the cosmos. When we recognize that Atlas might be related to a comet seen in 1840, we're doing something uniquely human, finding patterns across scales of time that dwarf individual lifetimes, building knowledge that transcends generations, creating meaning from observation and analysis. The fragmentation of Atlas, which seemed like a disappointment at the time, becomes in this context a gift. We were privileged to witness the continuation of a process that might have begun thousands of years ago, to see with our own instruments what previous generations could only imagine. The comet came apart before our eyes, but in doing so it revealed its nature, its fragility, its connection to deep time. Each fragment that drifted away carried with it a piece of the story, ensuring that the legacy of the parent comet would continue into the future. The message in the ancient ice of Atlas, the water, the organic molecules, the dust from other stars, reminds us that we're not separate from the cosmos, but part of it. The atoms in our bodies have been on journeys that make our human travel seem insignificant. They've been forged in stellar furnaces, dispersed in supernova explosions, gathered into new stars and planets, possibly stored in comets for billions of years, delivered to Earth, and eventually assembled into us. When we observe a comet, we're looking at our extended family, distant cousins made of the same star stuff, following different paths but sharing the same ultimate origin. The Oort cloud, that vast, dark nursery where Atlas spent most of its existence, remains largely mysterious. We've never seen it directly, probably never will, yet we know it's there from the comets it sends us. It's a perfect metaphor for so much of our understanding of the universe, inferred from indirect evidence, understood through its effects rather than direct observation, more vast and strange than our everyday experience can easily comprehend. The Oort cloud reminds us that most of the universe is hidden from us, dark and distant, revealing itself only through messengers like Atlas that briefly enter our small sphere of awareness. As we think about the future, about the comets yet to come, about the fragments still approaching, we're reminded that we're living in the middle of an ongoing story. The solar system isn't a static stage on which events occur, but a dynamic, evolving system, where processes that began billions of years ago continue today and will continue billions of years into the future. Comets will keep falling from the Oort cloud, fragmenting, sublimating, delivering their ancient materials to the inner solar system. Planets will continue their orbits, gradually evolving under tidal forces and solar radiation. The sun itself will age, eventually expanding to consume the inner planets, then shrinking to a white dwarf, gradually cooling over trillions of years. In this vast temporal context, the appearance of Atlas in 2020 and the Great Comet of 1844 are barely distinguishable. Two brief flickers of light separated by an instant of cosmic time. Yet from our human perspective, embedded in the flow of much shorter timescales, these events are separated by generations, by the rise and fall of nations, by transformations in human understanding and capability. This tension between cosmic and human timescales is part of what makes comets so fascinating. They're accessible to human observation, yet they operate on timescales that transcend human experience. The question of whether Atlas was known before it was found turns out to have multiple answers, each true in its own way. In the most literal sense, Atlas as a distinct comet was unknown until 2020. But if it's indeed a fragment of a comet that also produced the Great Comet of 1844, then in a sense we've been observing pieces of the same object across centuries without realizing it, and in the deepest sense Atlas has been known since the beginning, its orbit determined by the laws of physics, its eventual appearance in our skies as inevitable as the sunrise, just waiting for the right moment, the right observers, the right understanding to recognize it for what it was. This multiplicity of answers reflects the complexity of the universe and our evolving understanding of it. Simple questions lead to complex explorations. Straightforward observations reveal deep connections. Individual events turn out to be part of vast patterns. The story of Atlas and its possible connection to the Great Comet of 1844 is just one thread in the tapestry of cosmic evolution. But following that thread has led us through the entire history of the solar system, from its formation to its eventual end. The beauty of this unfinished story lies partly in its incompleteness. We don't have all the answers, can't prove definitively that Atlas and the Great Comet of 1844 are related, don't know when or if other fragments will appear. This uncertainty isn't a failure of science, but its strength. It means there's more to discover, more to learn, more to wonder about. Future comets will bring new data, new mysteries, new connections to explore. Future generations will have their own questions, their own tools, their own moments of discovery and wonder. As you drift towards sleep tonight, perhaps you can imagine yourself floating in space, watching the slow dance of comets around the sun. See them not as isolated objects, but as part of a vast interconnected system, messengers from the edge of the solar system carrying news of our cosmic origins. Think of Atlas, now dispersed into fragments too faint to see, its message delivered, its ancient ice returning to space. Think of the Great Comet of 1844, inspiring wonder in a world lit by gaslight, its observers unaware they might be seeing a sibling of a comet that would appear 176 years later. Think of the parent comet, that hypothetical mountain of ice that broke apart long ago, scattering its fragments across the centuries. Each piece carries the same message, the same ancient materials, the same connection to the birth of our solar system. Some fragments have already passed through our skies, observed and recorded. Others are still approaching, their arrival years or centuries in the future. Still others may have been destroyed, sublimated away entirely, or fallen into the sun, their messages lost forever. But the story continues whether we're watching or not. Comets keep falling from the Oort cloud, following their ancient orbits, carrying their cargo of ice and dust and organic molecules. The solar system keeps evolving, slowly but inexorably, following the laws of physics that have governed it since the beginning. And somewhere in all this cosmic machinery, on a small planet orbiting an ordinary star, consciousness has emerged with the capacity to observe, to wonder, to understand. We are the universe becoming aware of itself, as Carl Sagan said, and comets like Atlas are part of how we achieve that awareness. The connection between Atlas and the Great Comet of 1844, whether proven or not, reminds us that we're embedded in deep time, that the present moment is connected to the distant past and far future in ways we're only beginning to understand. Every comet we see has a history stretching back billions of years, and a future extending forward until the sun dies. We glimpse them only briefly, during their short passages through the inner solar system, but those glimpses connect us to the vast scales of space and time that define our universe. So the story of Atlas is not really about a single comet that appeared in 2020 and then fragmented. It's about the continuity of matter and motion across cosmic time, about the patient accumulation of human knowledge across generations, about our growing understanding of our place in the universe. It's about ancient ice carrying messages from the birth of the solar system, about fragments of a parent comet returning across centuries, about the Oort cloud waiting in darkness at the edge of our cosmic neighborhood. Most of all, it's about wonder, the wonder that comets have always inspired, that they continue to inspire, that they will inspire in future generations who look up and see these ancient travelers crossing their skies. Atlas may have disappointed those hoping for a spectacular sight, but it gave us something perhaps more valuable. A connection to deep time, a puzzle to solve, a reminder of the complexity and beauty of the cosmos. In its fragmentation, in its connection to historical comets, in its origin in the Oort cloud, Atlas told us a story about ourselves, about our origins, about our place in the vast dance of matter and energy that we call the universe. The question we began with, was Atlas known before it was found, has no simple answer, because it opens into these vast spaces of time and possibility, but perhaps that's the point. The best questions aren't those with simple answers, but those that lead us on journeys of discovery, that connect seemingly disparate phenomena, that reveal the deep patterns underlying surface appearances. Atlas led us on such a journey from 22 back to 1844, from Earth to the Oort cloud, from a single comet to a family of fragments, from a moment of observation to the entire history of the solar system, and the journey continues. Tomorrow night, and the night after, and thousands of nights into the future, comets will trace their paths across the sky. Most will be too faint to see without telescopes, but each one carries the same ancient message, the same connection to our cosmic origins. Some might be fragments of the same parent that gave us Atlas and the Great Comet of 1844. Others will be new visitors, approaching the sun for the first time in human history. All of them will be reminders that we live in a universe of constant motion and change, where ancient ice falls from the darkness to briefly grace our skies with light. The story has no ending because the cosmos has no ending, only transformation, evolution, the endless dance of matter and energy according to the laws of physics. Atlas has transformed from a single comet into multiple fragments, from fragments into dispersed molecules and dust, from a discrete object into part of the diffuse matter of the solar system. But the atoms that composed it continue, will always continue following new paths, perhaps one day to be gathered into new comets, new planets, new possibilities we can't imagine. In this endless transformation lies a kind of immortality. The parent comet that might have produced Atlas and the great comet of 1844 no longer exists as a single object, but it persists in its fragments, in the meteors that might one day streak through our atmosphere, in the water and organic molecules delivered to planets, in the scientific knowledge gained from their observation. Nothing is truly lost, only transformed, recycled, reborn in new forms. This is the ultimate message of our cosmic mystery, that we're part of something immeasurably vast and ancient, something that transcends our brief individual existence, something beautiful in its complexity and profound in its implications. When we look at a comet, we're looking at our past and our future simultaneously, at where we came from and where we're going, at the temporary made eternal through constant change. Sleep now, if you're ready, carrying with you these images of ancient ice and patient orbits, of fragments spreading across centuries, of messages written in molecules and delivered across billions of years. Let your dreams drift among the comets, out to the Oort cloud, where trillions of potential visitors wait in darkness, back to the early solar system when everything was forming, forward to future nights when new comets will grace new skies. You are part of this story, made of the same materials, governed by the same laws, participating in the same cosmic dance. The mystery continues, will always continue, each answer opening new questions, each observation revealing new wonders. Atlas came and went, fragments and fades, but its story goes on in the scientific papers written about it, in the memories of those who observed it, in the fragments still orbiting the sun, in the questions it raised about its connection to other comets. The great comet of 1844 blazed across 19th century skies and passed into history, but its legacy continues in the observations recorded by long-dead astronomers, in its possible connection to Atlas, in the ongoing search for other family members. And somewhere out there, perhaps already falling toward the sun, perhaps still orbiting peacefully in the Oort cloud, are other fragments of the parent comet, other chapters of this story waiting to be written. They'll arrive in their own time, be observed by future generations, add their pieces to the puzzle. The story we've traced tonight is just one small part of a much larger narrative, one that includes every comet, every planet, every star, every galaxy, all connected by the same physical laws, all participating in the same cosmic evolution. Rest now in the knowledge that you're part of this grand story, that the atoms in your body have been on incredible journeys, that you're connected to every comet that has ever graced Earth's skies, and every one that ever will. The universe continues its patient spinning, comets continue their ancient orbits, and somewhere in the darkness, ancient ice carries messages that we're only beginning to learn how to read. The mystery of Atlas, whether it was known before it was found, becomes just one note in this vast cosmic symphony, beautiful in itself but gaining its full meaning only in relation to all the others, past and future, known and unknown, forever unfolding in the darkness and the light.